Hello there, and welcome to Midnight Sleep Science. Tonight you are floating, not in a dream, but in a place where floating is the most natural thing in the world. You are suspended in the International Space Station, 350 kilometers above Earth, moving at 28,000 kilometers per hour, and yet you feel nothing. No wind, no speed, no pull, just stillness. This is what astronauts describe when they first enter orbit. A silence so complete, it changes how they understand their own bodies. You are weightless, but gravity has not disappeared. It pulls on you just as strongly as it does on the ground below. The difference is that you are falling, continuously, endlessly, falling around the Earth at exactly the right speed to never hit it. This is the paradox of space. Gravity is everywhere, yet weightlessness exists. Tonight, we will explore this strange, beautiful truth, not through imagination, but through the real physics that governs every object in the universe. From the way your heart pumps blood in zero gravity, to the invisible forces bending space-time itself, we will move slowly through the science of falling, floating, and the delicate dance between mass and motion. Let yourself relax. Let curiosity guide you gently into the quiet mystery of what it truly means to be adrift in the void. If you enjoy these gentle journeys, feel free to like and subscribe. But for now, let's begin. You close your eyes and imagine the moment. The rocket has fallen away, the engines have stopped, and suddenly you feel nothing. Your arms drift upward without effort. Your legs lift from the floor. You open your eyes and see a pen floating in front of your face, suspended in the air as if held by invisible hands. This is your first moment in space. This is weightlessness. But something surprising is happening. Gravity has not disappeared. Right now, 400 kilometers above the surface of Earth, gravity pulls on you with almost the same strength it did on the ground. Scientists have measured it carefully. At the altitude of the International Space Station, gravity is still about 90% as strong as it is at sea level. If you could somehow stand on a platform at this height, you would feel only slightly lighter than usual. Yet here you are, floating, completely weightless. How can both things be true? The answer is simple, and it changes everything. You are falling, not in the way you fall when you trip or stumble, but in a continuous, endless fall that never reaches the ground. The International Space Station is falling toward Earth right now, and so are you. Gravity pulls you downward with immense force, accelerating you toward the planet's center at nearly the same rate it would if you jumped from a plane. But you never get closer. This happens because the station is also moving forward, incredibly fast, 28,000 kilometers per hour. At this speed, the station travels so quickly that as it falls toward Earth, the planet's curved surface falls away beneath it at exactly the same rate. Imagine throwing a ball horizontally. It curves downward as gravity pulls it, and eventually it hits the ground. Now imagine throwing it faster. It travels farther before landing. Faster still, and it goes even farther. At a certain speed, the exact speed the space station maintains, the ball would curve downward at the same rate the Earth curves away, and it would never touch the ground. It would fall around the Earth forever. This is orbit. Not an escape from gravity, but a perfect balance between falling and moving. You are not floating because gravity is weak. You are floating because you and everything around you are falling together. When astronauts first experience this, their bodies react with confusion. On Earth, your inner ear contains tiny structures called the vestibular system, fluid-filled canals, and calcium carbonate crystals, called otoliths, that sense gravity and motion. When you tilt your head, the fluid shifts. When you stand, the crystals press downward. These sensations tell your brain which way is up, how fast you are moving, and whether you are still or falling. Your vestibular system has been calibrated by gravity your entire life. In orbit, that calibration becomes meaningless. The crystals in your inner ear no longer press in any direction. The fluid no longer shifts when you turn your head. Your vestibular system sends signals that say you are falling, but your eyes see that you are not moving toward the ground. Your brain receives contradictory information, and it struggles to make sense of it. Many astronauts, nearly half, experience space adaptation syndrome in the first few days. They feel dizzy, disoriented, nauseous. Their sense of balance disappears because balance, as they have always known it, depends on gravity. But the human body is adaptable. Within days, the brain begins to reweight its sensory inputs. It learns to trust vision more than the vestibular system. It updates its internal model of how movement should feel in this new environment. The cerebellum, a region at the back of the brain, adjusts its predictions about the consequences of motion. This adaptation happens quickly. Significant changes occur within 24 hours, and the process stabilizes after about 5 days. The nausea fades. The dizziness stops. Astronauts begin to move with grace and confidence, gliding through the station as if they were born to float. Yet something essential has changed. When you float in the station, there is no up or down. The floor is wherever you place your feet. The ceiling is wherever you look. Astronauts sleep strapped to walls because it makes no difference whether their heads point toward Earth or away from it. Orientation becomes arbitrary. Direction becomes meaningless. You learn to navigate by landmarks, not by the pull of gravity. You become a creature of 3 dimensions, free from the vertical axis that dominated your existence on Earth. This sense of perpetual falling creates something unexpected, a kind of freedom. On Earth, every movement requires effort against gravity. When you lift your arm, you fight the downward pull. When you stand, your muscles work constantly to keep you upright. Your bones bear the weight of your body, compressing slightly with every step. Your heart pumps blood upward against gravity's resistance, working harder to supply your brain with oxygen. But in orbit, all of this effort vanishes. You can move with the lightest touch. A gentle push against a wall sends you gliding across the entire length of the station. You can spin in place with a flick of your wrist. Your muscles no longer strain to hold you upright because there is no upright to maintain. Yet this freedom comes with a strange cost. Your body begins to forget what it means to resist. Without the constant pull of gravity, your muscles start to weaken. Your bones, no longer bearing load, begin to lose density. Astronauts on long missions can lose up to 1% of their bone mass per month in weightlessness, particularly in the hips, spine, and legs, the regions that normally carry the body's weight. The body is efficient. It does not maintain what it does not need. In the absence of gravity, it quietly dismantles the structures built to resist it. But before those changes accumulate, there is simply the experience, the sensation of floating. You push gently off a wall and drift forward, your body rotating slowly in the air. You see the Earth passing beneath you through the station's windows. Blue oceans, white clouds, the thin, bright line of the atmosphere glowing at the edge of the planet. You are moving at 28,000 kilometers per hour, yet you feel no speed. The station moves with you. The air moves with you. Everything around you falls together, synchronized perfectly in this endless plunge around the world. This is what physicists call free fall, the state of motion when gravity is the only force acting on an object. On Earth, true free fall is rare and brief. A skydiver experiences it for a few seconds before air resistance builds up and creates drag. A person jumping from a diving board feels it for a fraction of a second before hitting the water. But in orbit, free fall continues indefinitely because there is no air to slow you down, no ground to stop you. The mathematics of this are elegant. Gravity accelerates all objects at the same rate, regardless of their mass. A feather and a hammer, dropped in a vacuum, fall at exactly the same speed. Astronauts on the Moon demonstrated this in one of the most beautiful experiments ever conducted, dropping both objects simultaneously and watching them hit the surface together. In orbit, you and the station fall at the same rate. You do not float away from the walls because you are not moving relative to them. Everything inside the station shares the same trajectory through space, the same curve through the gravity well surrounding Earth. This is why weightlessness is sometimes called microgravity rather than zero gravity. Gravity is still present, it is still pulling, but because everything is falling together, you cannot feel it. Weight is not the presence of gravity, it is the sensation of resisting gravity. When you stand on the ground, the floor pushes upward against your feet. and you feel that pressure as weight. In orbit, nothing pushes against you. You fall freely, and so you feel nothing at all. It is a strange paradox. To be weightless, you must be falling. To float, you must be in motion, and to orbit Earth, you must move so fast that you fall around the planet rather than toward it. The sensation astronauts describe is not one of rising or hovering, but of constant, gentle descent. Except the descent never ends, and the ground never arrives, and so you float. Days pass in this state. Weeks. You learn to sleep while drifting, strapped loosely to a wall so you do not bump into equipment during the night. You learn to eat food that hovers in front of your mouth, guiding it carefully with your hands, because dropping it means it will simply hang in the air where it left your fingers. You learn to drink water that forms into spheres and wobbles with surface tension, clinging to itself in the absence of any force to pull it down. Every action requires relearning. On Earth, pouring water from a bottle into a cup is automatic. Gravity does the work. In orbit, water does not pour. It clings to the bottle's opening, reluctant to leave, held by molecular forces stronger than the absent pull of weight. You must coax it out, squeeze it gently, and guide it through the air. Even walking becomes meaningless. There is no point in lifting your legs and setting them down when there is no floor pressing against your feet. Instead, you push off surfaces and glide, using handrails to redirect your momentum, moving through the station like a swimmer moving through water, except the medium is not water, but simply the absence of resistance. This is what astronauts mean when they say that space changes them. Not metaphorically, but physically. Their relationship with the most fundamental force in their lives, the force that shaped their skeleton, their muscles, their sense of direction, is suddenly interrupted. They discover that what they thought was solid and permanent was actually conditional. Gravity was always there, invisible and unquestioned, like the air they breathed. And now it is still there, pulling just as hard, but its effects have vanished because they are in perfect synchrony with its pull. This reveals something profound. Gravity is not a force that pushes you into the ground. It is a force that accelerates you downward. The ground, in turn, pushes upward, and that upward push is what creates the sensation of weight. Remove the ground, and the sensation disappears, even though gravity remains. This is why astronauts feel weightless while falling. This is why a person in an elevator that suddenly drops experiences a brief moment of lightness before the cables catch. In that instant, they are falling freely, and their body cannot distinguish between that fall and the sensation of floating in space. Albert Einstein understood this deeply. He called it the equivalence principle, the idea that gravitational acceleration and the acceleration caused by motion are indistinguishable from each other. If you were inside a closed box with no windows, you could not tell whether the box was sitting on Earth's surface, with gravity pulling you down, or accelerating upward through space at exactly 9.8 meters per second squared, creating an identical sensation of weight. Both situations feel the same. Both press your feet against the floor with the same force. The experience is equivalent, and this equivalence points towards something even stranger. Gravity, Einstein realized, is not simply a force pulling objects together. It is something deeper, something woven into the structure of space itself. When you float in orbit, you are not defying gravity. You are following it perfectly. You are tracing the natural path that objects take when no other forces interfere. That path curves because space itself curves, and understanding why space curves, why gravity bends the universe around massive objects like Earth, requires looking at the fabric of reality itself, at the geometry that underlies everything you see and feel. You close your eyes again, floating in the station, feeling the gentle absence of weight, and you begin to wonder what gravity truly is, if it can exist without being felt. What invisible architecture holds you in orbit, keeps the moon circling Earth, and guides every falling object through the cosmos? You have learned what it feels like to fall forever. Now you need to understand why. What is gravity really? For centuries, people believed it was a force, an invisible pull between objects with mass, reaching across empty space to draw them together. Isaac Newton described it that way. An apple falls because Earth pulls it downward. The moon orbits because Earth's gravity reaches out and holds it in place. This explanation worked beautifully for 300 years. It predicted the motion of planets with astonishing accuracy, but it left questions unanswered. How does gravity reach across the void? How does Earth pull on the moon without touching it, without any medium connecting them? Newton himself admitted he could not explain the mechanism. He could describe what gravity did, but not what it was. The answer came in 1915, when Albert Einstein published his general theory of relativity. And what he proposed was so strange, so fundamentally different from Newton's vision, that it changed the way humanity understood the universe. Einstein said that gravity is not a force at all. It is geometry. It is the shape of space itself, curved and warped by the presence of mass. Imagine a flat rubber sheet stretched tight. If you place a heavy ball in the center, the sheet bends downward, creating a depression. Now roll a smaller ball across the sheet. It does not travel in a straight line. It curves inward, following the shape of the depression created by the heavier ball. This is what mass does to space. Earth sits in the universe like the heavy ball on the rubber sheet, and space curves around it. You, floating in orbit, are not being pulled toward Earth. You are following the natural curve of space. In flat, undistorted space, objects move in straight lines, but near a massive object like Earth, space is not flat. It bends, and when you move through bent space, your path bends too. This is why planets orbit stars, why moons orbit planets, why you orbit Earth. You are all following the curves that mass creates in the fabric of space-time. Space-time. That word is important. Einstein realized that space and time are not separate. They are woven together into a single four-dimensional structure. You move through space, but you also move through time. Every moment, you travel 1 second into the future. And just as mass curves space, it also curves time. Near a massive object, time flows more slowly. Clocks on Earth's surface tick slightly slower than clocks in orbit. The difference is tiny, only a few microseconds per day. But it is real and measurable and necessary to account for when calibrating GPS satellites. This curvature is invisible. You cannot see it or touch it, but you can feel its effects every time you drop an object, every time you feel weight beneath your feet, every time you watch the moon rise. Gravity is the sensation of moving through curved space-time. When you stand on Earth's surface, you are trying to move along the curve that Earth creates, but the ground stops you. The ground pushes upward, preventing you from following your natural path through space-time, and you feel that resistance as weight. In orbit, there is no ground to stop you. You follow the curve freely, and so you feel nothing. This is why weightlessness and free fall are the same thing. You are not escaping gravity. You are surrendering to it completely, letting it guide your motion without resistance. The space station curves through space-time, and you curve with it, synchronized perfectly to the shape that Earth's mass imposes on the universe around you. Einstein's insight emerged from a thought experiment. He imagined a person standing in an elevator. If the elevator were sitting still on Earth's surface, the person would feel their weight pressing down through their feet. Now imagine the elevator cable snaps. As the elevator falls, the person inside becomes weightless. They float, just like an astronaut in orbit. But here is the crucial question. If the person has no windows, no way to see outside, can they tell the difference between floating in a falling elevator and floating in deep space, far from any gravitational source? Einstein realized they cannot. The two situations are physically identical. This told him something profound about the nature of gravity itself. If falling feels the same as floating in empty space, then gravity cannot be a force pulling you down. Instead, what we call gravity must be the natural motion of objects through space-time when no forces act on them. On Earth's surface, you are not sitting still. You are constantly trying to move along a curved path through space-time, following the natural geometry that Earth's mass creates. But the ground prevents you from following that path. The ground pushes upward, and that upward push is what creates the sensation of weight. Remove the ground, and you fall freely, following the curve without resistance. This is why physicists say that objects in free fall are actually moving in straight lines. They are geodesics, the straightest possible paths through curved space-time. It sounds paradoxical. How can a falling apple be moving in a straight line? The answer is that space-time near Earth is curved, and in curved geometry, straight lines look curved to outside observers. Imagine drawing a straight line on a flat piece of paper. Now curve that paper into a cylinder. The line you drew, which was perfectly straight on the flat surface, now appears to curve around the cylinder. Nothing about the line itself changed. Only the geometry of the space containing it changed. Earth curves space-time in a similar way. The more massive an object, the more it curves the space around it. The Sun curves space-time much more than Earth does. A neutron star curves it even more dramatically. And at the extreme, a black hole curves space-time so severely that not even light can escape from within a certain radius. Each of these objects creates a different shape in the fabric of the universe, and other objects respond by following the contours of that shape. You can visualize this, though imperfectly. Picture a bowling ball placed on a trampoline. The fabric stretches downward, creating a depression. Now roll a marble across the trampoline. It curves inward toward the bowling ball. Not because the bowling ball pulls it, but because the marble follows the slope of the stretched fabric. This analogy has limitations. It suggests gravity pulls downward, which is not quite right. But it captures the essential idea. Mass distorts geometry, and objects move according to that distortion. The mathematics describing this distortion are Einstein's field equations, a set of 10 interrelated equations that relate the curvature of space-time to the distribution of matter and energy within it. These equations predict phenomena that Newton's laws could not explain. They predict that clocks run slower in strong gravitational fields, that light bends when passing near massive objects, and that gravitational waves, ripples in space-time itself, propagate outward when massive objects accelerate. All of these predictions have been confirmed by observation. Right now, as you float in the space station, you are following a geodesic through the curved space-time surrounding Earth. Your trajectory looks like a circle from the outside, but from your perspective, you are simply moving forward through space, with no forces acting on you except the occasional push off a wall or the gentle thrust of the station's engines to maintain altitude. The curvature itself guides your motion, bending your path into a closed loop around the planet. This understanding of gravity as curved geometry leads to something even more remarkable. If mass curves space-time, and if massive objects move through that curved space, then space-time itself can ripple. These ripples are called gravitational waves, disturbances in the fabric of the universe that travel outward at the speed of light. Einstein predicted them in 1916, just months after publishing his general theory of relativity, but he doubted they could ever be detected. The ripples would be extraordinarily faint. A gravitational wave passing through Earth would compress and stretch space by a distance smaller than the width of a single proton. Yet scientists persisted. In the 1960s, physicist Joseph Weber built massive aluminum cylinders weighing 3,000 kilograms, designed to vibrate when gravitational waves passed through them. He placed two detectors nearly 1,000 kilometers apart and connected them by phone line to filter out local disturbances like storms or earthquakes. In 1969, Weber announced he had detected gravitational waves, but when other teams built similar detectors, they found nothing. Weber's signals were likely false, caused by vibrations or electronic noise. The search continued for decades. Engineers developed a different approach, laser interferometers that split beams of light and sent them down long perpendicular tunnels. When the beams returned and recombined, any difference in their arrival time would reveal that space-time had been stretched or compressed along one path more than the other. The concept was proposed in the 1960s by several physicists independently, and prototypes were built in the 1970s by Robert Forward and Rainer Weiss. By 1990, plans were approved for the Laser Interferometer Gravitational Wave Observatory, LIGO, consisting of two detectors with arms 4 kilometers long, one in Louisiana and one in Washington state. For years they detected nothing. The instruments were upgraded, made more sensitive, shielded from vibrations caused by traffic, airplanes and distant earthquakes. And then, on September 14, 2015, both detectors registered the same signal within 7 milliseconds of each other. The signal lasted only a fraction of a second, increasing in frequency from 35 to 250 Hz as it rose in strength. The source was a collision between two black holes, each roughly 30 times the mass of the Sun, merging together 1.3 billion light-years away. During the final moments of the merger, the system released more power than all the stars in the observable universe combined. 3 solar masses of energy converted directly into gravitational waves, sending ripples through space-time that traveled outward in all directions. When those ripples reached Earth, they compressed and stretched space by a distance 10,000 times smaller than the width of a proton. But LIGO detected them. This detection confirmed what Einstein had predicted nearly a century earlier. Space-time is not static. It can bend, ripple, and vibrate. Massive objects moving through it create waves that propagate across the universe, carrying information about collisions and catastrophes in the distant cosmos. And now, floating in the space station, you are a part of that same curved geometry. Earth's mass bends space-time around you, and you follow that curve, tracing a path that loops endlessly around the planet. But why does your orbit remain stable? What keeps you circling at this exact altitude, this exact speed? The answer lies in a delicate balance between motion and gravity, a balance so precise that even a small change in velocity would send you spiraling, either outward into deep space or downward toward Earth's atmosphere. You have been floating for hours now, drifting through the modules of the International Space Station, and you begin to notice something remarkable. Despite the absence of weight, despite the sensation of endless falling, you remain at precisely the same altitude above Earth's surface, 400 kilometers. No higher, no lower. Well, not quite. The station descends slowly, losing about 100 meters each day. But for now, you circle the planet in a stable loop that repeats itself every 90 minutes. How does this happen? Why does the station not spiral inward toward Earth's atmosphere, or drift outward into the emptiness of deep space? The answer lies in motion. The space station is moving extraordinarily fast, 7.6 kilometers per second, which translates to roughly 28,000 kilometers per hour. At this speed, you travel the entire circumference of Earth in about 90 minutes. This velocity is not arbitrary. It is the exact speed required at this altitude to balance the inward pull of gravity with the outward momentum of your motion. Move any slower, and gravity wins. You fall toward Earth. Move any faster, and momentum wins. You climb to a higher orbit or escape entirely. This balance is sometimes described as a tug-of-war between two forces, gravity pulling you inward and centrifugal force pushing you outward. But that description, while intuitive, is not quite accurate. Centrifugal force is not a real force. It is an apparent force that arises when you observe motion from a rotating reference frame. What actually happens is simpler and more elegant. Gravity continuously accelerates you toward Earth's center, changing the direction of your velocity without changing its magnitude. You fall sideways as much as you fall downward. And because Earth's surface curves away beneath you at exactly the same rate, you never get closer to the ground. Imagine standing on a perfectly flat plane and throwing a ball horizontally. Gravity pulls it downward, and it arcs toward the ground. Now imagine throwing it faster. The arc becomes longer, shallower. Throw it fast enough, impossibly fast from a human perspective, and the ball travels so far horizontally that Earth's curvature becomes significant. The ground begins to fall away beneath the ball at nearly the same rate gravity pulls it down. At a certain critical speed, these two rates match perfectly, and the ball never lands. It falls continuously in a closed loop around the planet. This is orbit. Not a suspension of gravity, but a perfect harmony between falling and moving. The space station does not resist gravity, it surrenders to it completely, following the natural curve that gravity creates in space-time. but doing so at a velocity that keeps that curve circular rather than linear. Every object in orbit around Earth, satellites, debris, astronauts, shares this same principle. They are all falling, and they are all moving forward fast enough that their fall never ends. The mathematics describing this balance were worked out centuries ago by Isaac Newton, who imagined a cannon placed on top of a mountain tall enough to rise above Earth's atmosphere. Fire the cannonball horizontally with too little speed, and it falls to the ground nearby. Fire it faster, and it travels farther before landing. Fire it fast enough, and it circles the entire planet and returns to the mountain. An orbit. Newton never witnessed this himself, of course. The technology did not exist in his time, but he understood the principle, and he calculated the mathematics that govern it. Those calculations are surprisingly straightforward. The orbital velocity, the speed required to maintain a circular orbit, depends on only two things: the mass of the planet and the distance from its center. For Earth, at the altitude where the space station flies, that velocity is approximately 7.6 kilometers per second. Higher up, where the pull of gravity weakens slightly with distance, the required velocity decreases. Lower down, closer to Earth's surface where gravity is stronger, the required velocity increases. This relationship between altitude and velocity reveals something fundamental about orbits. The closer you are to Earth, the faster you must move to stay in orbit. At the altitude where the space station flies, roughly 400 kilometers above sea level, you complete one orbit every 90 minutes. Higher up, at 36,000 kilometers, satellites move more slowly and take exactly 24 hours to complete one orbit, remaining fixed above the same point on Earth's surface. These are called geostationary satellites, and they appear motionless in the sky because they orbit at exactly the same rate Earth rotates. But the space station does not orbit in a perfect vacuum. Even at 400 kilometers altitude, traces of Earth's atmosphere remain. Thin wisps of nitrogen, oxygen, and other gases that have diffused upward from the denser layers below. These molecules are sparse, perhaps a few trillion per cubic meter compared to the trillions of trillions at sea level, but they are enough to create drag. Every atom the station collides with slows it down slightly, stealing a tiny fraction of its momentum. Over days and weeks, this drag accumulates. The station loses altitude, descending roughly 100 meters each day. This descent is slow but relentless. If left unchecked, the station would eventually spiral inward, entering denser and denser layers of atmosphere until drag became overwhelming and the structure began to burn from friction with the air. To prevent this, the station must periodically boost itself back to a higher altitude. These maneuvers are called reboosts, and they are performed using thrusters, either the station's own propulsion systems or engines attached to visiting spacecraft, particularly Russian Progress resupply vehicles that dock with the station several times each year. A reboost is simple in principle. The thrusters fire, pushing the station forward along its orbital path. This increases velocity, and with greater velocity comes a higher orbit. The process takes only minutes, but it is carefully calculated. Engineers on the ground track the station's position and velocity continuously, predicting when the altitude will drop below acceptable limits and scheduling a reboost accordingly. The frequency of these maneuvers varies. Sometimes weeks pass between reboosts. Other times they occur more frequently depending on solar activity. Solar activity matters because the sun's output is not constant. During periods of high solar activity, times when solar flares and coronal mass ejections are common, Earth's upper atmosphere absorbs more energy and expands outward. This expansion increases atmospheric density at the station's altitude, creating more drag and forcing more frequent reboosts. During quieter solar periods, the atmosphere contracts, drag decreases, and the station coasts for longer intervals between altitude corrections. You do not feel these reboosts, not in the way you would feel acceleration on Earth. The thrust is gentle, adding only a few meters per second to the station's velocity over the course of several minutes. Objects continue to float. Your body remains weightless. The station simply climbs, slowly and imperceptibly, back to its operational altitude. And then the thrusters shut off, and you continue falling around the planet, tracing the same endless curve through space. This delicate dance between motion and gravity, between falling and flying, is what keeps every satellite in orbit. It is what allows telecommunications networks to function, weather forecasts to remain accurate, and navigation systems to guide travelers across Earth's surface. Thousands of objects circle the planet right now, each one locked into its own unique balance between velocity and altitude, each one falling perpetually without ever touching the ground. And so the station falls, endlessly looping around Earth, completing one orbit every 90 minutes. This means that during a typical day aboard the station, you circle the planet 16 times. You witness 16 sunrises and 16 sunsets, each one lasting only a few minutes as the station passes from darkness into light and back again. The sun appears at the horizon, climbs briefly, and then sinks away. 45 minutes later, it rises again. This rapid cycling makes it difficult to maintain any natural sense of day or night. To compensate, astronauts follow a schedule based on Greenwich Mean Time, dividing their day into structured segments that mimic life on Earth. They wake at 6 in the morning, not because the sun has risen, but because Mission Control says it is morning. They sleep for 8 hours at the end of each day, using blindfolds or closing the shutters on their cabin windows to block the sunlight that continues to stream through every 90 minutes. Without this imposed structure, the constant alternation between light and dark would make sleep nearly impossible. The daily routine is meticulously planned. Schedules are broken down into 5-minute increments, with every task assigned a specific time slot. Morning begins with hygiene, brushing teeth with edible toothpaste that must be swallowed because there is no sink to spit into, washing with rinseless shampoo and damp towels, checking the day's assignments sent overnight by Mission Control. Then comes breakfast, followed by a morning conference call with ground teams in Houston and Munich to discuss the day's work. The work itself varies. Astronauts spend roughly half their time conducting scientific experiments, growing plants in controlled chambers, studying how flames behave in microgravity, monitoring their own bodies to understand how weightlessness affects bone density, muscle mass, and cardiovascular function. The other half is devoted to maintenance. The station is a complex machine, and it requires constant attention. Air filters must be cleaned, computer systems must be updated, equipment must be inspected, repaired, or replaced. Sometimes this work requires a spacewalk, exiting the station through an airlock, tethered by safety cables, to replace batteries or install new hardware on the exterior hull. And always, there is exercise. 2 hours every day, mandatory, using a treadmill, a stationary bicycle, and resistance equipment designed to simulate weight training. Without this exercise, muscles atrophy rapidly in the absence of gravity's constant pull. Bones lose density. The heart weakens because it no longer needs to pump blood upward against resistance. The body is efficient. It adapts to its environment. And in an environment where weight does not exist, the body quietly dismantles the structures built to resist it. But despite the routine, despite the schedules and the structure, there is always the awareness of motion. You are falling, continuously. The station races forward at nearly 8 kilometers every second, tracing its endless curve around the planet. You pass over oceans, continents, cities glowing in the night. You cross the Terminator, the line dividing day from night, 16 times in 24 hours. Below you, Earth rotates slowly, while you circle it at a speed that makes a complete revolution seem brief, almost fleeting. This is the reality of orbit. Not stillness, but perpetual motion. Not escape from gravity, but perfect surrender to it. And as you float through the station, your body adapting moment by moment to this strange new existence, you begin to notice changes. Subtle at first, then unmistakable. Your face feels different, slightly swollen. Your sinuses feel congested, as if you have a mild cold, though you are not sick. When you look in a mirror, you notice that your face appears puffy, rounder than usual, and your neck seems thicker. This is one of the first changes astronauts notice when they arrive in orbit. A shift in how their body distributes fluid. On Earth, gravity pulls blood and other fluids downward. Your heart works against this constant pull, pumping blood upward to supply your brain with oxygen and nutrients. The vessels in your legs expand slightly to accommodate the extra fluid that accumulates there over the course of a day. This is why ankles sometimes swell after standing for hours, and why lying down at night feels restful. It allows fluid to redistribute more evenly throughout the body. In orbit, that downward pull disappears. Blood and lymphatic fluid no longer pool in the lower body. Instead, they shift upward, moving into the chest, neck, and head. Within hours of arriving at the space station, roughly 2 liters of fluid, about half a gallon, migrate from the legs into the upper body. This redistribution creates the puffy face that astronauts call moon face or puffy head bird leg syndrome. Because while the face swells, the legs become noticeably thinner. Your body interprets this fluid shift as a problem. Sensors in the heart and major blood vessels detect the increased volume in the upper body and send signals to the kidneys, instructing them to eliminate excess fluid. Over the next few days, the kidneys respond by producing more urine. Astronauts lose up to 20% of their total blood volume during the first week in space as the body adjusts to what it perceives as fluid overload. This is not dangerous, but it does create changes. The blood becomes slightly thicker, more concentrated. The heart, which no longer needs to work as hard to pump blood upward, begins to shrink slightly, losing muscle mass just as other muscles do when they are no longer required to work against resistance. Your spine begins to change too. On Earth, gravity compresses the vertebrae in your back throughout the day. The cartilage discs between each vertebra bear weight, flattening slightly under the constant load. At night, when you lie down, the compression eases and the discs expand, which is why people are slightly taller in the morning than in the evening, typically by about 1 to 2 centimeters. In orbit, this compression never happens. The spine is free to extend fully, and the cartilage discs expand without ever being compressed by weight. Over the course of days and weeks, astronauts grow taller, not dramatically, but measurably. Most gain between 5 and 8 centimeters in height during a long mission. This elongation is painless at first, but many astronauts experience back pain as the muscles and ligaments surrounding the spine stretch to accommodate the new length. Some describe it as a persistent ache, similar to growing pains. Others say it feels like their back is being gently pulled apart. But the most profound changes happen deeper inside the body, in places where the effects are invisible but significant. Without gravity constantly loading the skeleton, bones begin to lose density. On Earth, bones are living tissues that constantly remodel themselves. Cells called osteoblasts build new bone, while cells called osteoclasts break down old bone. This process is regulated by mechanical stress, the pressure and tension that bones experience when they bear weight. When bones are loaded, osteoblasts become more active, building denser, stronger structures. When bones are not loaded, osteoclasts dominate, breaking down bone faster than it is replaced. In orbit, bones experience almost no loading. Astronauts can lose up to 1 to 2% of their bone mass per month, particularly in weight-bearing regions like the hips, spine, and legs. This loss is similar to what happens in osteoporosis, a condition common in older adults, but it occurs much faster in space. After 6 months in orbit, an astronaut might lose as much bone density as a postmenopausal woman would lose in several years. The calcium released from deteriorating bones does not simply disappear. It enters the bloodstream, circulating through the body and eventually being filtered by the kidneys. Elevated calcium levels in the urine increase the risk of kidney stones forming, a painful and potentially dangerous condition in space where medical treatment options are limited. Some astronauts take medications to help reduce calcium loss and all drink extra water to keep the kidneys flushed and minimize stone formation. muscles weaken too. On Earth, every moment spent standing, walking, or simply holding your body upright requires muscular effort. Your legs support your weight. Your back and core muscles stabilize your spine. Your heart pumps blood against gravity's resistance. In orbit, these demands vanish. Muscles that once worked constantly now rest, and the body, always efficient, begins to dismantle what it no longer needs. The muscles most affected are those responsible for posture: the calves, thighs, back, and neck. These muscles can lose up to 20% of their mass in just 2 weeks of weightlessness. Over 3 to 6 months, the loss can reach 30%. What took years to build through exercise and daily activity can atrophy in weeks when gravity no longer provides resistance. Astronauts describe the sensation of weakness when they first return to Earth. Legs that feel heavy and unresponsive, backs that struggle to support the body's weight, a profound exhaustion that comes from simply standing upright. To slow this deterioration, astronauts exercise rigorously, 2.5 hours every day. They run on treadmills equipped with harnesses that pull them downward, simulating the feeling of weight. They pedal stationary bicycles. They use resistance machines that provide the mechanical stress muscles need to maintain strength. But even this intense regimen cannot fully prevent the loss. The body knows it is not truly bearing weight, and it responds accordingly. The cardiovascular system changes as well. Your heart, a muscle like any other, adapts to the reduced workload. Without gravity pulling blood downward, the heart does not need to pump as forcefully. Over weeks and months, it becomes slightly smaller, losing muscle mass in the left ventricle, the chamber responsible for pumping oxygenated blood throughout the body. Blood pressure regulation shifts. The vessels that normally constrict and dilate to maintain steady pressure despite changes in posture lose some of their responsiveness. Arterial stiffness increases during long missions. Studies have shown that after 6 months in space, the stiffness of major arteries rises by 17 to 30% compared to pre-flight measurements. This stiffening resembles changes seen with aging and may contribute to cardiovascular problems later in life. The body produces fewer red blood cells in microgravity, leading to a condition called space anemia. Approximately 10% of red blood cells are destroyed shortly after arriving in orbit, and production does not fully compensate for the loss. Even the immune system is affected. Research shows that immune function becomes suppressed during spaceflight, making astronauts more susceptible to infections. Bacteria aboard the station become more virulent in the microgravity environment, growing faster and developing increased resistance to antibiotics. Dormant viruses in the body, like herpes simplex, can reactivate as the immune system weakens. And then there are the changes that remain invisible until astronauts return home. The vestibular system, having adapted to weightlessness, must recalibrate once again to Earth's gravity. Balance and coordination suffer for days or weeks. Walking feels strange. Turning the head too quickly triggers dizziness. The brain must relearn how to interpret signals from the inner ear, how to predict the consequences of movement, how to stand without falling. Some effects linger even longer. Vision problems have emerged as one of the most concerning long-term consequences of spaceflight. The fluid shift that creates the puffy face also increases pressure inside the skull, pushing against the back of the eyeball and causing it to flatten slightly. The optic nerve can swell. Some astronauts develop permanent changes in their vision, requiring corrective lenses even years after returning to Earth. Recovery takes time. For every month spent in space, it takes roughly 2 to 3 months on Earth for bone density to return to normal levels. Some astronauts need up to 4 years to fully recover their skeletal strength. Muscle mass returns more quickly, but cardiovascular fitness and coordination require months of rehabilitation. Yet the body is remarkably adaptable. These changes, profound as they are, represent the body's attempt to optimize itself for a new environment. Within days of arriving in orbit, the cardiovascular system begins recalibrating. The heart adjusts its output to match the reduced demands of pumping blood in weightlessness. The kidneys establish a new equilibrium for fluid balance. The brain rewires its neural pathways, learning to interpret sensory information in the absence of gravitational cues. Research has revealed changes even at the molecular level. In a remarkable study of identical twin astronauts Scott and Mark Kelly, scientists compared their genetics after Scott spent nearly a year aboard the International Space Station while Mark remained on Earth. Upon Scott's return in 2016, genetic analysis found that approximately 1,000 of his genes expressed themselves differently than his twin brothers. Changes related to DNA repair, immune function, bone formation, and cellular stress responses. Most of these changes reverted to normal within months of returning to Earth, but some persisted longer, suggesting that spaceflight leaves lasting molecular signatures in the body. The brain itself undergoes structural changes. MRI scans of astronauts before and after long missions reveal that certain brain regions expand while others compress. The cerebellum, responsible for coordinating movement, shows decreased connectivity with motor areas of the cerebral cortex. The vestibular cortex, which processes balance and spatial orientation, demonstrates reduced activity. These alterations reflect the brain's attempt to adapt to an environment where traditional concepts of up and down no longer apply. Even the microbiome, the trillions of bacteria living in the digestive system, changes in space. Studies have shown that the composition of gut bacteria shifts during spaceflight, with some species becoming more abundant while others decline. The reasons for these changes are not fully understood, but they may relate to altered immune function, dietary differences, or the stress of living in a confined environment. Psychological effects emerge as well. Living in isolation, confined to a small space with the same handful of people for months, separated from family and friends by hundreds of kilometers of vacuum, creates mental strain. Sleep disturbances are common due to the rapid day-night cycles and the constant hum of machinery. Some astronauts report mood changes, difficulty concentrating, and feelings of isolation despite being in constant communication with ground control. Yet when astronauts return to Earth, most of these changes gradually reverse. The puffy face deflates as fluids redistribute downward. Muscles rebuild with exercise. Bones slowly regain density, though this process can take years. The vestibular system recalibrates to Earth's gravity. Balance returns, and the strange sensation of heaviness eventually feels normal again. The body remembers Earth, and given time, it returns to the configuration shaped by millions of years of evolution under gravity's constant pull. But while the body adapts and changes inside the station, outside the hull lies an environment far more extreme. Beyond the thin aluminum walls separating you from the void, conditions exist that the human body cannot tolerate even briefly. No air, no pressure. Temperatures that swing from searing heat to numbing cold. This is the vacuum of space. Not truly empty, but close enough to emptiness that nothing familiar can survive there unprotected. Outside the International Space Station, beyond the aluminum hull that separates you from the void, lies an environment fundamentally incompatible with human life. The vacuum of space, the word itself suggests emptiness, a complete absence of matter, a nothingness waiting just beyond the walls. But this is not quite accurate. Space is not truly empty. It contains traces of hydrogen, helium, and other elements scattered so thinly that a cubic meter might hold only a few atoms. Electromagnetic radiation passes through it constantly. Visible light from stars, infrared warmth, ultraviolet rays, cosmic radiation. Gravitational fields permeate it. Magnetic fields twist and bend through it. Space is better described not as empty, but as nearly empty. A vacuum so close to perfect that the differences become meaningful. On Earth, at sea level, air presses against every surface of the body with a force of approximately 100,000 pascals, about 14.5 pounds per square inch. This pressure is constant, equal on all sides, and the body has evolved to function within it. The gases in the lungs, the fluids in the bloodstream, the tissues throughout the body, all exist in equilibrium with this atmospheric pressure. Remove that pressure suddenly and the equilibrium breaks. In space, atmospheric pressure does not exist. The pressure is effectively zero, or more precisely, less than 1/1,000,000,000th of Earth's surface pressure. If a person were exposed to this vacuum without protection, the consequences would unfold rapidly and in a specific sequence that researchers have documented through tragic accidents and controlled experiments. The first effect would be the loss of air from the lungs. Within a fraction of a second, the pressure differential between the gases inside the body and the vacuum outside would force air outward through the mouth and nose. Even holding the breath would not prevent this. The pressure difference is too great to resist. The air would rush out violently, emptying the lungs completely. With the lungs emptied, oxygen stops entering the bloodstream. The blood already circulating continues to deliver oxygen to the brain for a brief period, approximately 9 to 12 seconds, before the deoxygenated blood arrives. During those seconds, consciousness remains, though confusion and panic would likely dominate the experience. After 10 to 15 seconds, oxygen deprivation causes unconsciousness. The person would collapse, unaware of what happens next. Simultaneously, a condition called ebulism would begin. At pressures below approximately 6,000 pascals, an altitude of about 19 kilometers on Earth, known as the Armstrong limit, water in the body begins to vaporize. The boiling point of water depends on pressure. At sea level, water boils at 100 degrees Celsius. At lower pressures, it boils at lower temperatures. In the near vacuum of space, water boils at body temperature. Saliva on the tongue would bubble and evaporate. Moisture in the eyes, nose, and respiratory tract would begin to boil. Jim LeBlanc, a NASA test subject who accidentally experienced rapid depressurization during a 1966 experiment in a vacuum chamber, later recalled feeling the saliva on his tongue start to bubble just before he lost consciousness. As water vaporizes from the tissues, it draws heat away through evaporative cooling. The mouth and respiratory tract would cool rapidly, approaching freezing temperatures as moisture continuously boils away. The rest of the body would cool more slowly because evaporation occurs primarily at surfaces exposed to the vacuum. The vaporization of water within bodily fluids would cause tissues to swell. Gas bubbles would form in the bloodstream and within cells, a process similar to decompression sickness experienced by divers who ascend too quickly. The body could bloat to nearly twice its normal size as these bubbles expanded, though the skin and tissues are elastic and porous enough to prevent rupturing. Blood circulation would slow as expanding gases blocked vessels, and the heart would struggle to pump blood past these vapor locks. However, if rescued quickly, the damage would not be immediately fatal. Studies and accidental exposures have shown that a person could survive approximately 90 seconds of vacuum exposure if returned to pressure within that window, though the experience would cause severe injury. The longest documented accidental exposure occurred during the 1966 NASA vacuum chamber test, when Jim LeBlanc's suit depressurized at an altitude equivalent of 36 kilometers. He lost consciousness after about 14 seconds and was repressurized within 30 seconds. He recovered fully with no lasting damage. This demonstrates that the human body, while vulnerable to vacuum, does not explode or freeze instantly as popular culture often depicts. Against these dangers, the spacesuit provides a portable environment, a wearable spacecraft that maintains pressure, supplies oxygen, regulates temperature, and shields against radiation. The suit is essentially a pressurized vessel, maintaining an internal atmosphere of pure oxygen at about 4.3 pounds per square inch, roughly 1/3 of Earth's sea level pressure. This lower pressure makes the suit easier to move in, because higher pressure would cause the suit to become rigid and resist bending. Astronauts breathe pure oxygen for hours before a spacewalk to purge nitrogen from their blood and prevent decompression sickness when transitioning to the lower pressure environment. The suit itself consists of multiple layers, each serving a specific function. Closest to the skin, astronauts wear a liquid cooling and ventilation garment, a network of thin tubes woven into fabric through which chilled water circulates, carrying heat away from the body. Outside this lies the pressure bladder, a rubber-like airtight layer that holds the oxygen atmosphere inside the suit. The bladder is surrounded by a restraint layer made of strong fabric that gives the suit its shape and prevents it from ballooning outward like an overfilled balloon. The restraint layer includes carefully designed joints with folds and gauze that allow the astronaut to bend arms and legs despite the internal pressure working against movement. Beyond the pressure layers comes the thermal micrometeoroid garment, consisting of multiple layers of aluminized insulation and tough fabrics like Kevlar or Dacron. These outer layers protect against temperature extremes and micrometeorites, tiny particles of rock and metal traveling at speeds up to 27,000 kilometers per hour. A collision with even a small particle at such velocity could puncture the suit, causing rapid depressurization. The layered construction distributes the energy of impacts and prevents penetration. Temperature regulation is critical. In direct sunlight, surfaces exposed to the sun can reach 121 degrees Celsius. In shadow, temperatures plunge to -156 degrees Celsius. The suit's insulation layers, combined with the liquid cooling system and reflective outer surfaces, maintain a comfortable temperature inside, without convection to transfer heat. Since there is no air to carry warmth away, the suit must rely on radiation and conduction through the cooling garment to prevent overheating. The life support system, carried in a backpack called the primary life support system, supplies oxygen, removes carbon dioxide through chemical scrubbers, circulates cooling water, and powers communications equipment. This system allows astronauts to work outside the station for up to 8 hours before returning to replenish consumables. The entire assembly weighs roughly 130 kilograms on Earth, though it feels weightless in orbit. Testing these suits requires simulating the vacuum of space on Earth. Engineers place suits in massive vacuum chambers where pumps evacuate air until pressure drops to levels, matching those found hundreds of kilometers above the surface. In these chambers, pressure reaches 10 to the power of -7 to 10 to the power of -12 millibars, an ultra-high vacuum approaching the emptiness of space itself. Astronauts train in these chambers, learning how the suit behaves when all external pressure vanishes and the fabric stiffens against their movements. Yet, despite these protective layers, astronauts do venture outside. They exit through airlocks, small chambers with 2 sealed doors that allow passage from the pressurized interior of the station to the vacuum beyond without losing the atmosphere inside. The process is methodical and cannot be rushed. At least 24 hours before a spacewalk, the entire crew begins breathing an atmosphere with slightly elevated oxygen levels, while the station's pressure is reduced from normal atmospheric pressure to 70 kilopascals. This gradual reduction allows nitrogen dissolved in the bloodstream to dissipate slowly, preventing it from forming bubbles when the astronaut later transitions to the suit's lower pressure environment. 1 hour before exiting, the astronaut dons a mask and breathes pure oxygen, further purging nitrogen from the tissues. Then comes the suit itself, a process that takes nearly an hour, with each component checked and rechecked. Once sealed inside, the astronaut enters the airlock, a cylindrical chamber barely 1.6 meters in diameter and 2 meters high. The inner hatch closes. The airlock depressurizes gradually until its pressure matches the vacuum outside. Only then does the outer hatch open, revealing the void. Exiting feels surreal. There is no wind, no sound except the hum of the suit's ventilation system and the crackle of the radio connecting the astronaut to the station and mission control. Moving requires effort because the pressurized suit resists bending at every joint. Gloves stiffen, making delicate work with tools challenging. Fingers tire quickly from the constant squeezing needed to grip objects. Yet the view is incomparable. Earth fills half the sky, rotating slowly beneath. The sun, unfiltered by atmosphere, blazes with an intensity that would damage unprotected eyes instantly. Tethers keep astronauts connected to the station. Steel cables clip to attachment points on the hull. These lifelines prevent drift. If an astronaut were to lose grip and float away untethered, returning would require the safer system, simplified aid for EVA rescue, a small jetpack worn on the lower back that uses nitrogen gas thrusters controlled by a joystick. This system has never been needed in an emergency, but astronauts train extensively with it, learning to navigate in 3 dimensions using short, controlled bursts. Spacewalks last 6 to 8 hours on average, though the longest on record stretched to 8 hours and 56 minutes during a 2001 mission when astronauts remained suited in the airlock, ready to exit again if robotic operations encountered problems. During these hours, astronauts perform maintenance, replacing batteries, installing new equipment, repairing damaged components, conducting experiments that require direct exposure to the space environment. Every movement is planned in advance, choreographed in training pools on Earth where neutral buoyancy simulates weightlessness. As of late 2021, 245 spacewalks had been conducted at the International Space Station, totaling over 1,500 hours of work in the vacuum. Each one follows strict protocols. Each one carries risks. Tools are tethered because a dropped wrench becomes orbital debris, circling Earth at thousands of kilometers per hour. Contamination from leaking coolant requires careful decontamination procedures before re-entering the station. Visors can fog, gloves can leak, equipment can fail, but the work continues. Humans venture into an environment fundamentally hostile to life, protected by fabric and technology, falling around Earth while repairing the platform that keeps them alive. And when the work is done, they retreat back through the airlock, sealing the outer hatch, repressurizing the chamber, and returning to the relative safety of the station's interior. Beyond those walls, the vacuum remains, patient, empty, and utterly indifferent to the fragile creatures moving through it. The space station continues its endless fall around Earth, but Earth itself is falling too, not toward the ground. There is no ground beneath a planet, but through the curved space-time surrounding the Sun. Right now, as you float in orbit, Earth moves through space at nearly 30 kilometers per second, tracing a vast ellipse that takes 1 year to complete. This is Earth's orbit, and it follows the same principles that keep you circling the planet below. Gravity curves space-time. Objects follow those curves, and when the curves are just right, falling becomes circling. The solar system is a collection of falling objects, each one locked into its own trajectory through the gravitational landscape created by the Sun. 8 planets, hundreds of moons, thousands of asteroids, millions of comets, all of them follow paths determined by mass, distance, and velocity. None of them sit still. None of them resist gravity. They surrender to it completely, and in surrendering, they create the stable, predictable dance that has continued for billions of years. Mercury, closest to the Sun, moves fastest. It completes one orbit in only 88 Earth days, racing around the Sun at 47 kilometers per second. This speed is necessary. The Sun's gravity is strongest near its surface, and objects close to the Sun must move quickly to avoid spiraling inward. Mercury's orbit is not a perfect circle. It is an ellipse, stretched slightly so that at its closest approach, Mercury comes within 46 million kilometers of the Sun, and at its farthest, it reaches nearly 70 million kilometers away. This variation is subtle but measurable, and it reveals something fundamental about how gravity works across distance. Venus follows farther out, taking 225 days to complete its orbit at a more leisurely 35 kilometers per second. Then comes Earth, circling at nearly 30 kilometers per second, completing one orbit in 365 days. Mars orbits beyond Earth slower still at 24 kilometers per second, taking 687 days to circle the Sun. Each planet moves at precisely the speed required to balance the Sun's gravitational pull at that distance. Move faster, and the planet would climb to a higher orbit or escape entirely. Move slower, and it would fall inward toward the Sun. This relationship between distance and orbital speed was first described mathematically by Johannes Kepler in the early 17th century, decades before Newton developed his theory of gravity. Kepler studied decades of precise astronomical observations made by Tycho Brahe tracking the positions of planets night after night, year after year. From this data, Kepler extracted patterns. He discovered that planets move faster when closer to the Sun and slower when farther away. He found that the time required to complete one orbit is related to the average distance from the Sun by a precise mathematical ratio. The square of the orbital period is proportional to the cube of the average distance. This relationship, now called Kepler's third law, applies to every object orbiting the Sun, from Mercury to distant Neptune. Beyond Mars lies the asteroid belt, a region populated by thousands of rocky fragments, ranging from boulders to objects hundreds of kilometers across. Most asteroids orbit between 2 and 3 astronomical units from the Sun. An astronomical unit being the average distance from Earth to the Sun, approximately 150 million kilometers. These asteroids move at speeds between 15 and 25 kilometers per second, each one following its own elliptical path through the gravitational landscape. Jupiter dominates the outer solar system. With a mass 318 times that of Earth, Jupiter is massive enough to create its own significant gravitational field. It orbits the Sun at a distance of about 5 astronomical units, taking nearly 12 Earth years to complete one circuit. Its orbital velocity is 13 kilometers per second, slow compared to the inner planets, but appropriate for its distance from the Sun. Jupiter's gravity is strong enough to capture dozens of moons. The largest, Ganymede, is bigger than Mercury and orbits Jupiter every 7 days. The smallest known moons are only 1 or 2 kilometers across and take more than 2 years to complete one orbit at the outer edges of Jupiter's gravitational influence. Saturn follows Jupiter, orbiting at 9.5 astronomical units from the Sun, taking 29 Earth years to complete one revolution at a stately 9.5 kilometers per second. Like Jupiter, Saturn is a gas giant with its own system of moons. At least 146 confirmed satellites orbiting within its gravitational domain. The largest, Titan, is bigger than Mercury and possesses a thick nitrogen atmosphere, making it one of the most Earth-like worlds in the solar system, despite its frigid surface temperature of -180 degrees Celsius. These moons orbit Saturn according to the same gravitational principles that govern the planets around the Sun. Closer moons move faster. Distant moons move slowly. Each one traces an ellipse through Saturn's gravitational field. The 4 largest moons of Jupiter, Io, Europa, Ganymede and Callisto, discovered by Galileo Galilei in 1610, demonstrate orbital mechanics on a smaller scale. Io, closest to Jupiter, completes one orbit every 42 hours, racing around the planet at 17 kilometers per second. Europa orbits slightly farther out, taking 3.5 days to circle Jupiter. Ganymede requires 7 days, and Callisto takes 17 days to complete its orbit. The first 3 of these moons are locked in what astronomers call orbital resonance. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This synchronization, known as the Laplace resonance, arose through gravitational interactions over millions of years and remains stable, each moon's orbit reinforcing the others. Jupiter possesses 97 confirmed moons as of 2025, though astronomers expect hundreds more await discovery. Small irregular objects captured by Jupiter's gravity from solar orbits and shattered into fragments through collisions. The innermost moons, including Métis and Adrastea, orbit so close to Jupiter that they complete one revolution in less than 8 hours, faster than Jupiter itself rotates. These moons exist within the Roche limit, the distance at which tidal forces from Jupiter exceed the moon's internal cohesion. Eventually, these moons will break apart, ground to dust, by the very gravity that holds them in orbit. The outer moons follow highly elliptical paths, some reaching more than 20 million kilometers from Jupiter at their farthest point. Many orbit retrograde, opposite to Jupiter's rotation, a configuration that provides greater orbital stability according to computer models. All of Jupiter's moons are tidally locked, meaning they rotate at the same rate they orbit, keeping one face permanently toward Jupiter just as Earth's moon keeps one face toward Earth. Beyond Saturn lie Uranus and Neptune, ice giants orbiting in the outer reaches of the solar system. Uranus circles the Sun at 19 astronomical units, taking 84 Earth years to complete one orbit. Neptune, most distant of the major planets, orbits at 30 astronomical units, requiring 165 Earth years for a single revolution. Neptune's orbital velocity has slowed to just 5 kilometers per second, 1/10 the speed of Mercury, because the Sun's gravitational influence weakens with distance. Yet even at this distance, gravity remains dominant, curving space-time enough to hold Neptune in its orbit and prevent it from drifting into interstellar space. Beyond Neptune lies a vast region populated by smaller bodies, dwarf planets, asteroids, and comets that orbit in the cold outer reaches of the solar system. Pluto, once considered the 9th planet, now holds the designation of dwarf planet after astronomers realized it shares its orbital zone with thousands of similar objects. Pluto orbits at an average distance of 39.5 astronomical units from the Sun, taking 248 Earth years to complete one circuit. Its orbit is highly elliptical, bringing it as close as 30 astronomical units at perihelion, closer to the Sun than Neptune, and carrying it out to nearly 50 astronomical units at aphelion. Pluto is not alone in the outer darkness. Eris orbits even farther out, averaging 68 astronomical units from the Sun and requiring 557 Earth years for one complete revolution. Makemake and Haumea follow similarly distant paths, each taking centuries to circle the Sun once. These objects belong to the Kuiper Belt, a region extending beyond Neptune that contains thousands of icy bodies ranging from small rocks to objects comparable in size to Pluto. All of them follow the same gravitational principles that govern the major planets. Distance determines orbital period. Mass and velocity determine the shape of the orbit. Closer to the Sun, between Mars and Jupiter, lies Ceres, the only dwarf planet in the inner solar system. Ceres orbits at 2.77 astronomical units, embedded within the asteroid belt, and completes one orbit every 4.6 Earth years. Despite being the largest object in the asteroid belt, Ceres measures only 950 kilometers across, small enough that its entire volume would fit within the borders of Alaska. Yet it possesses enough mass to have pulled itself into a spherical shape through its own gravity, a characteristic that distinguishes dwarf planets from irregular asteroids. All these objects, planets, dwarf planets, moons, asteroids, demonstrate the same fundamental relationship between gravity and motion. Every one of them falls continuously through the curved space-time surrounding the Sun or their parent planet. The closer they are to the massive body they orbit, the faster they must move to maintain a stable path. The farther away they drift, the more slowly they travel, following wider, more leisurely curves through space. This balance has persisted for billions of years, since the solar system formed from a rotating disk of gas and dust surrounding the young Sun. The stability of these orbits is not absolute. Gravitational interactions between planets create subtle perturbations. Jupiter's massive gravity influences the orbits of asteroids and comets, sometimes ejecting them from the solar system entirely or redirecting them toward the inner planets. Neptune's gravity shapes the outer edge of the Kuiper Belt, preventing objects beyond a certain distance from accumulating into larger bodies. Over millions of years, these interactions cause orbits to shift slightly, planets to migrate inward or outward by small amounts, and small bodies to collide or be expelled. Yet despite these changes, the overall architecture remains stable. The Sun's gravity dominates, the planets continue their ancient paths, moons circle their parent worlds, and through it all, nothing resists gravity. Nothing struggles against the curve of space-time. Every object simply follows the natural path laid out by the distribution of mass throughout the solar system. This is the choreography of falling. Billions of objects synchronized by the invisible geometry of curved space, each one tracing its trajectory through the gravitational landscape that the sun creates simply by existing. You have been falling for weeks now, circling Earth in the endless plunge that defines orbit. But what does it truly mean to fall? On Earth, the word carries specific associations. The sensation of dropping, the rush of air, the approaching ground, the inevitable impact. In space, falling feels different, gentler, continuous. Yet the physics underlying both experiences is identical. Whether plummeting from an airplane or floating in the space station, the same fundamental principles govern the motion. Free fall is the state of motion, when gravity is the only force acting on an object. No air resistance, no surface pushing upward, no thrust from engines, only gravity pulling the object along the natural curve of space-time. On Earth, true free fall is rare because air resistance begins almost immediately when an object moves through the atmosphere. A skydiver leaping from an airplane experiences pure free fall for only the first few seconds before air molecules accumulate below, creating drag that opposes the downward motion. Within 10 to 15 seconds, the skydiver reaches terminal velocity, the speed at which air resistance exactly balances gravitational acceleration, preventing any further increase in speed. At that point, free fall ends. The skydiver is no longer accelerating. Gravity still pulls downward, but air pushes upward with equal force, and the net effect is zero. The sensation changes. Instead of weightlessness, the skydiver feels pressure from below, as if lying on an invisible cushion of air. This is not free fall anymore. It is simply falling at a constant speed through a fluid medium. But in those first seconds, before air resistance builds, the skydiver experiences something close to what astronauts feel continuously. The stomach rises into the chest. The arms float upward without effort. There is no sense of speed, no wind initially, just the strange absence of weight as the body accelerates downward at 9.8 meters per second squared. Earth's gravitational acceleration. This acceleration is constant for all objects near Earth's surface, regardless of their mass. A feather and a hammer, dropped simultaneously in a vacuum, fall at exactly the same rate and hit the ground at the same moment. This principle, that all objects fall at the same rate in a gravitational field, was first demonstrated by Galileo Galilei in the late 16th century. Legend says he dropped objects of different masses from the Leaning Tower of Pisa to prove that weight does not affect the rate of fall, though historians doubt this specific story. What is certain is that Galileo performed careful experiments, rolling balls down inclined planes, measuring their acceleration and demonstrating that mass does not influence how quickly objects accelerate under gravity. The reason for this uniformity is fundamental to how gravity works. Gravitational force is proportional to mass. A heavier object experiences more gravitational pull than a lighter one. But acceleration depends on the ratio of force to mass. When force increases in proportion to mass, the ratio remains constant, and so does the acceleration. A bowling ball experiences more gravitational force than a tennis ball, but it also has more mass to accelerate. The two effects cancel exactly, resulting in identical acceleration for both objects. In 1971, astronaut David Scott demonstrated this principle on the Moon, where the airless environment provides a perfect vacuum for free-fall experiments. Standing on the lunar surface during the Apollo 15 mission, Scott held a geological hammer in one hand and a falcon feather in the other. He released them simultaneously, and both objects fell to the ground at precisely the same rate, touching down at the same instant. The demonstration, broadcast live to Earth, provided visual proof of Galileo's insight. In the absence of air resistance, all objects fall equally. You, floating in the space station, are experiencing this same principle, extended indefinitely. You fall at exactly the same rate as the station itself, which is why you remain motionless relative to its walls. If the station were smaller, say, the size of a single room, and if you floated at one end while a colleague floated at the other, both of you would fall toward Earth at infinitesimally different rates because one person would be slightly closer to Earth's center than the other. Over time, this difference would cause a slow drift, bringing you together. But the station is large enough and the difference small enough that the effect remains negligible during normal operations. This difference in gravitational pull across distance is called a tidal effect, and it becomes significant only when objects are very large or very close to massive gravitating bodies. For the human body, floating in orbit 400 kilometers above Earth, the tidal force is negligible. The difference in gravitational acceleration between your head and your feet amounts to only a few millionths of a meter per second squared. You cannot feel it. But near more massive objects, or across greater distances, tidal forces become powerful enough to stretch and compress matter. The experience of free fall, whether in an airplane or in orbit, reveals something profound about gravity. When no forces oppose gravitational acceleration, weight disappears entirely. This suggests that weight is not an intrinsic property of matter, but rather a consequence of resistance to gravity. The ground creates weight by pushing upward. Remove the ground, and weight vanishes, even though gravity remains. This insight applies universally. Every object in free fall experiences weightlessness, regardless of where it falls or how fast it moves. A person in an elevator whose cable has snapped feels the same weightlessness as an astronaut in orbit, even though the elevator occupies a very different position in Earth's gravitational field. The sensation depends not on the strength of gravity, but on whether anything opposes gravity's pull. Engineers use this principle to create brief periods of weightlessness on Earth. Aircraft fly in parabolic arcs, climbing steeply and then diving, in a carefully controlled trajectory that matches the natural curve of free fall. During the dive, which lasts 20 to 30 seconds, everything inside the aircraft, passengers, equipment, floating water droplets, experiences true free fall. The aircraft and its contents all accelerate downward at the same rate, creating the same weightless environment found in orbit. Astronauts train in these aircraft, practicing movements and procedures in microgravity before venturing into space. The physics of free fall also explains why orbits are stable. An object in orbit is in perpetual free fall, but its forward velocity ensures that it falls around the planet rather than into it. The trajectory curves continuously, matching the curvature of the planet below, so the distance between the orbiting object and the surface remains constant. Change that velocity even slightly, and the orbit changes. Increase speed, and the object climbs to a higher altitude. Decrease speed, and it descends. This relationship between velocity and altitude is quantified by the vis-viva equation, a fundamental formula in orbital mechanics that relates an object's speed at any point in its orbit to its distance from the central mass and the shape of its orbital path. The equation shows that orbital velocity decreases with altitude. Satellites closer to Earth must move faster than those farther away to maintain stable orbits. The International Space Station, at 400 kilometers altitude, travels at 7.7 kilometers per second. Satellites in geostationary orbit, at 36,000 kilometers altitude, move at only 3 kilometers per second. Energy governs these relationships. An orbiting object possesses both kinetic energy from its motion and gravitational potential, energy from its position in the gravitational field. The sum of these energies remains constant in a stable orbit, but the balance between them shifts continuously. As the object moves closer to the planet, potential energy decreases and kinetic energy increases. The object speeds up. As it moves farther away, potential energy increases and kinetic energy decreases, and the object slows down. This interplay creates the rhythm of elliptical orbits, where velocity varies throughout the path. You, floating in the station, embody these principles. You fall freely, experiencing no forces except gravity. Your weightlessness is not an absence of gravity, but a perfect surrender to it. And as you drift through the modules, objects around you behave in ways that seem impossible on Earth. Water forms spheres, air does not rise. Flames burn in strange, round shapes. This is microgravity, an environment where gravity exists, but produces no apparent weight, allowing other forces, normally overshadowed by gravity's dominance, to reveal themselves. The microgravity environment aboard the station allows scientists to observe phenomena that would be impossible to study on Earth. When gravity no longer dominates, other forces emerge from the background. Surface tension, normally a minor effect, compared to weight, becomes the primary force shaping liquids. Electrostatic attraction between objects, barely noticeable on Earth, can cause small items to cling together or drift toward charged surfaces. Convection, the upward flow of warm air and downward flow of cool air driven by density differences, ceases entirely because there is no up or down for buoyancy to follow. Flames burn differently in microgravity. On Earth, hot combustion gases rise due to buoyancy, drawing fresh oxygen in from below and creating the familiar teardrop shape of a candle flame. In orbit, hot gases do not rise. They remain near the flame, forming a spherical shell around the combustion zone. Oxygen must diffuse inward through this hot layer, making the burning process slower and less efficient. The flame becomes round, dimmer, and burns at a lower temperature than it would on Earth. Researchers study these microgravity flames to understand combustion processes more clearly, developing more efficient engines and safer fire suppression systems. Crystal growth experiments benefit from microgravity because crystals can form without being distorted by their own weight or disrupted by convection currents in the solutions surrounding them. Protein crystals grown in space tend to be larger and more uniform than those grown on Earth, making them easier to analyze using X-ray crystallography. This has helped researchers understand the three-dimensional structure of proteins involved in diseases, leading to the development of new pharmaceuticals. Materials. Science experiments take advantage of the absence of sedimentation, the tendency of denser materials to sink and lighter materials to float in a mixture. On Earth, when molten metals with different densities are combined, they separate as they cool, with heavier elements settling to the bottom. In microgravity, the materials remain mixed uniformly, allowing the creation of alloys and composite, materials with properties that cannot be achieved on Earth. Engineers have used these experiments to develop stronger, lighter materials for aerospace and industrial applications. Biological research reveals how living organisms respond to the absence of gravity. Plant roots, which normally grow downward, in response to gravitational cues, become disoriented in orbit. Some spiral in circles, others grow in random directions. Eventually, many adapt, using other cues like light, moisture, or chemical gradients to orient their growth. Understanding these adaptations is essential for developing life support systems that could grow food during long missions to Mars or beyond. Cells themselves change in microgravity. Studies have shown that the protein modifier called SUMO, small ubiquitin-like modifier, helps cells adapt to weightlessness by regulating stress responses, DNA repair, and cellular division. Gene expression shifts in microgravity, with some genes activating more strongly while others become less active. These molecular changes affect how cells grow, divide, and repair damage, with implications for wound healing, immune function, and long-term health during spaceflight. Living in free fall for weeks or months reveals that the human body is fundamentally designed for gravity. Every system, skeletal, muscular, cardiovascular, vestibular, evolved under constant gravitational load. Remove that load and the body adapts, but not always in beneficial ways. Yet the same environment that challenges human physiology also offers unique opportunities to observe physical and biological processes in ways impossible on Earth. Water behaves strangely when weight disappears. Liquids float, refusing to pour or settle. You squeeze a plastic pouch filled with water, and a sphere emerges. Not a droplet falling toward the floor, but a perfect globe hovering in the air, trembling slightly as it rotates. The sphere is nearly 3 centimeters across, large enough to see your reflection distorted on its curved surface. It floats between you and the far wall of the module, drifting slowly in whatever direction your squeeze imparted. This is water without weight. This is liquid freed from gravity's pull. On Earth, water pours. It flows downward, pulled by gravity into whatever container holds it. Surface tension exists, the cohesive force that holds water molecules together, but gravity overwhelms it for all but the smallest volumes. A droplet on a leaf might hold a spherical shape if it is small enough, but any larger volume succumbs to weight and flattens, spreads, or falls. In orbit, gravity no longer dominates. Surface tension becomes the primary force shaping liquids, and water behaves in ways that seem impossible. The sphere floating before you demonstrates this perfectly. Water molecules attract each other through hydrogen bonding. Each molecule's slightly positive hydrogen atoms pull toward neighboring molecules' slightly negative oxygen atoms. This attraction creates surface tension, the tendency of liquids to minimize their surface area. On Earth, gravity fights this tendency, pulling water downward and stretching it into streams and splashes. In microgravity, surface tension wins. Water contracts into the shape with the smallest possible surface area for a given volume. A sphere. You reach out and touch the sphere with your fingertip. It does not burst or splash. Instead, it clings to your finger, wrapping around it like a liquid glove. The water spreads across your skin, drawn by adhesion. The attraction between water molecules and the molecules of your skin. Without gravity to pull the water away, it simply stays there, coating your finger in a thin, trembling layer. You shake your hand gently, and the water redistributes but does not fly off. Only a strong flick will overcome the adhesive forces and send droplets spinning through the air. This behavior has practical consequences. Drinking water requires careful design. On Earth, pouring water into a cup and lifting it to your mouth is automatic. Gravity keeps the water in the cup. Tipping the cup causes water to flow toward your lips. In orbit, water does not stay in an open cup. It floats out, forming spheres that drift away. Astronauts drink through straws attached to sealed pouches, or from specially designed containers with capillary channels that guide liquid toward the mouth using surface tension alone. Washing becomes complicated. Water does not flow from a faucet into a sink. It emerges in spherical blobs that float through the air, colliding with surfaces and spreading across them in thin films. Astronauts wash with damp towels and rinseless soap, wiping their skin clean and allowing the towels to absorb moisture. Showers, as they exist on Earth, are impossible. The water would simply float in spheres throughout the enclosure, rather than falling downward and draining away. Tears behave strangely too. On Earth, tears form at the corner of the eye and run down the face, pulled by gravity. In orbit, tears accumulate around the eye, held by surface tension. They form a growing sphere of liquid that eventually becomes large enough to break free and float away. Astronauts describe the sensation as uncomfortable. The moisture builds up and does not drain naturally. Sometimes they must wipe tears away manually to clear their vision. Coffee presents its own challenges. Hot liquids release steam. water vapor that on Earth rises upward due to convection. In microgravity, steam does not rise. It remains suspended near the liquid surface, forming a cloud that drifts slowly through the air. If an astronaut opens a container of hot coffee carelessly, steam escapes in all directions, cooling rapidly and condensing into tiny droplets that float through the module like fog. The coffee itself must be drunk from a sealed pouch with a straw or from a specially designed cup that uses surface tension to draw liquid toward the rim where lips can reach it. Food preparation aboard the station is deliberately simple. Most meals arrive pre-cooked, freeze-dried, or thermostabilized, sealed in flexible pouches or rigid cans that require no refrigeration and can be stored for months or years. Freeze-dried. Foods are rehydrated by injecting water through a valve, then kneading the pouch to mix the contents. After waiting several minutes for water to absorb fully, the astronaut cuts open the pouch and eats directly from it using a spoon. Thermostabilized foods are heated in a small oven built into the galley, then eaten warm from their containers. Fresh food is rare. Fruits and vegetables arrive with resupply ships every few months, but without refrigeration, most spoil within days. Astronauts eat them quickly. Apples, oranges, tomatoes, savoring flavors that cannot be preserved through processing. These fresh items become special occasions, brief reminders of Earth's abundance. Carbonated beverages were attempted in the early days of spaceflight, but quickly abandoned. On Earth, gas and liquids separate in the stomach, with carbon dioxide rising to the top and escaping through burping. In microgravity, gas bubbles remain distributed throughout the liquid in the stomach, making burping impossible without also expelling liquid, a condition astronauts call wet burps. Coca-Cola and Pepsi were carried on a 1985 space shuttle mission in specially designed dispensers, but the experience was unpleasant enough that carbonated drinks are rarely requested now. Crumbs are forbidden. Bread, crackers, and any food that produces small particles becomes a hazard in microgravity. Crumbs float through the air, drifting into eyes, nostrils, and sensitive equipment. They can be inhaled accidentally, causing coughing or choking. They accumulate on air filters, reducing ventilation efficiency. For this reason, bread is replaced by tortillas, flexible, crumb-free wraps that can be filled with various ingredients and eaten without shedding particles. Tortillas have become a staple used for breakfast burritos, sandwich substitutes, and snacks. Salt and pepper are available only in liquid form. Sprinkling granular salt would send crystals floating through the cabin. Instead, astronauts use salt water and pepper oil, squeezing drops onto their food. These liquids adhere to the food through surface tension rather than falling away. Despite these adaptations, eating in space remains fundamentally different from eating on Earth. Food does not stay on plates. Liquids do not pour. Gravity's absence transforms every meal into a careful exercise in controlling substances that no longer obey familiar rules. Yet, astronauts adapt. They learn to guide floating spheres of juice toward their mouths. They become skilled at capturing drifting pieces of food mid-air. And they discover that surface tension, normally invisible beneath gravity's dominance, shapes the behavior of every liquid they encounter. Maintaining personal hygiene aboard the station requires creativity and adaptation. Bathing as it exists on Earth is impossible. Water supplies are limited, and more importantly, water does not flow downward into drains. Instead, astronauts take sponge baths, using one wet cloth to apply rinseless soap and another to wipe away excess moisture. The soap is specially formulated to work without rinsing. It breaks down oils and dirt without requiring large volumes of water to wash away. Hair washing follows a similar process. Astronauts apply rinseless shampoo directly to their scalp, massage it thoroughly, then towel dry their hair. The shampoo was originally developed for hospital patients unable to shower, and it works by encapsulating dirt and oils in a way that allows them to be wiped away mechanically rather than washed away with flowing water. After toweling the hair, simply air dries naturally, though this takes longer in the absence of convection currents that would accelerate evaporation on Earth. The station's toilet is perhaps the most complex system for managing fluids. On Earth, toilets rely on water and gravity to transport waste. In orbit, neither is available. Instead, the toilet uses airflow. Powerful fans create suction that draws waste into sealed containers. For urination, each astronaut has a personal funnel attached to a hose. The funnel's shape differs for male and female astronauts, but the principle remains the same. Suction pulls urine through the hose into a wastewater tank. The collected urine does not go to waste. It mixes with other wastewater from the station, condensation from the air, sweat absorbed by ventilation systems, even moisture from breath, and passes through a sophisticated purification system that recovers roughly 93% of it as drinkable water. Solid waste management is more involved. Astronauts position themselves over a small opening, much smaller than a typical toilet, and secure their legs with restraints to prevent floating away. The toilet uses airflow to pull waste into special bags that are sealed and stored in airtight containers. When the containers fill, they are loaded into unmanned cargo vehicles that undock from the station and burn up during re-entry into Earth's atmosphere. Even minor activities become exercises in fluid management. Brushing teeth requires swallowing the toothpaste rather than spitting, because saliva and foam would simply float through the cabin if expelled from the mouth. Shaving requires electric razors or razors with attached vacuum systems to capture loose hairs before they drift through the air and potentially enter eyes, nostrils, or sensitive equipment. Nail clipping is performed near air vents so that clippings are immediately drawn into filters rather than floating freely. Laundry does not exist. The water and equipment required to wash clothing in microgravity would be prohibitively expensive to launch and maintain. Instead, astronauts wear clothes until they become too dirty or develop odors, then dispose of them by packing them into cargo vehicles destined for re-entry and destruction. Underwear is changed approximately every 2 to 3 days. Shirts and pants are worn for about a week before disposal. Exercise clothing, which absorbs more sweat, is changed after each workout session. This accumulation of used clothing represents a significant mass that must be accounted for in mission planning. All these adaptations reveal how deeply humans rely on gravity for the most basic daily activities. Washing, drinking, eating, using the bathroom. Tasks so automatic on Earth that they require almost no conscious thought. Become deliberate, carefully choreographed procedures in orbit. Fluids behave according to principles rarely noticed in everyday life. Surface tension dominates. Adhesion and cohesion determine where liquids go and how they spread. And far below, on the planet circling beneath the station, another fluid responds to forces reaching across space. The ocean, pulled and shaped by the moon's gravity, rising and falling in the ancient rhythm of tides. You look through the window of the space station, and there it is, the moon, hanging in the darkness beyond Earth's curved horizon. From this vantage point, you can see both worlds at once. Earth fills most of your view, vast and blue, wrapped in swirling clouds. The moon appears smaller, grey and pockmarked, suspended in the black. They seem separate, isolated, but they are not. An invisible connection links them, stretching across the void. Gravity, reaching out from each world to grip the other, pulling them together across nearly 400,000 kilometers of empty space. This gravitational connection does more than keep the moon in orbit. It shapes Earth itself. Right now, as you watch from above, the moon's gravity is pulling on Earth's oceans, lifting them upward in a gentle bulge that follows the moon across the sky. Billions of tons of water rise and fall in response to this pull, creating the tides, the ancient rhythm that has governed coastlines for as long as liquid water has existed on Earth's surface. The mechanism is simple, though its effects are profound. Gravity weakens with distance. The side of Earth facing the Moon experiences slightly stronger gravitational pull than Earth's center, which in turn experiences stronger pull than the side facing away from the Moon. This difference, this gradient in gravitational force across Earth's diameter, is what creates tides. The water on the side nearest the Moon feels the strongest pull and rises upward, forming a bulge. The water on the opposite side, experiencing the weakest pull, also bulges outward, though for a different reason. It is left behind as Earth itself is pulled slightly toward the Moon. These two bulges, one facing the Moon, one facing away, create high tides. As Earth rotates beneath them, any given location on the surface passes through both bulges during a single day, experiencing two high tides roughly 12 hours apart. Between the bulges, water is pulled away, creating low tides. The entire cycle repeats approximately every 24 hours and 50 minutes. The time it takes for Earth to rotate enough to bring the same location back under the Moon, which has meanwhile moved slightly forward in its orbit. The tidal bulges are not large. In the open ocean, the difference between high and low tide amounts to only about half a meter. But near coastlines, where water funnels into bays and estuaries, the effect amplifies dramatically. The Bay of Fundy in Canada experiences tidal ranges exceeding 16 meters, the height of a 5-story building. Twice each day, water floods into the bay, filling inlets and covering mudflats. 6 hours later, it retreats, leaving boats stranded on the seafloor until the tide returns. The sun also contributes to tides, though its effect is weaker than the Moon's, despite its vastly greater mass. The sun sits 150 million kilometers away, nearly 400 times farther than the Moon. This distance reduces its tidal influence significantly. The sun's tidal force on Earth is only about 46% as strong as the Moon's. When the sun and Moon align, during new moons and full moons, their gravitational pulls combine, creating especially high spring tides. When they form a right angle, during quarter moons, their effects partially cancel, producing weaker neap tides. Tides affect more than just oceans. Earth's crust also rises and falls in response to the Moon's gravity, though the solid rock deforms much less than liquid water. The land beneath your feet rises approximately 30 centimeters twice each day as tidal forces squeeze and stretch the planet. These Earth tides are imperceptible to human senses, but measurable with sensitive instruments. Even the atmosphere experiences tides, with air pressure fluctuating slightly as gravitational forces redistribute atmospheric mass. The tides do more than move water. They transfer energy. As the tidal bulges sweep across Earth's surface, friction between moving water and the seafloor dissipates energy as heat. This friction acts like a brake on Earth's rotation, slowing it down by approximately 2 milliseconds per century. This deceleration is imperceptible on human timescales, but over millions of years it accumulates. Days are growing longer. 400 million years ago, during the Devonian period when the first forests appeared on land, Earth rotated faster, and days lasted only about 22 hours. The energy lost by Earth's rotation does not disappear. It transfers to the Moon, increasing its orbital energy and causing it to drift slowly outward, away from Earth. The Moon recedes at approximately 3.8 centimeters per year, about the rate fingernails grow. Laser ranging experiments, which bounce light off reflectors left on the lunar surface by Apollo astronauts, measure this drift with millimeter precision. The distance grows year by year, and as it does, the Moon's gravitational influence on Earth weakens slightly. This process has been ongoing for billions of years. When the Moon first formed, likely from debris ejected when a Mars-sized object collided with early Earth approximately 4.5 billion years ago, it orbited much closer, perhaps only 22,000 kilometers away compared to today's 384,000 kilometers. At that distance, tides would have been enormous, perhaps hundreds of meters high, surging across the primordial ocean with devastating force. Earth's rotation was also much faster, with days lasting only 5 hours. Over geological time, tidal friction has slowed Earth's spin and pushed the moon outward. The process continues today, though at a gradually decreasing rate as the moon's distance increases and its tidal influence weakens. Eventually, billions of years in the future, Earth and Moon will reach a stable configuration where both are tidally locked to each other. Earth's day will equal the Moon's orbital period, and the same face of Earth will always point toward the Moon, just as the same face of the Moon already points perpetually toward Earth. The Moon's tidal locking occurred much earlier in the solar system's history. When the Moon was younger and closer to Earth, tidal forces were strong enough to create significant bulges in the lunar crust. As the Moon rotated, these bulges shifted out of alignment with Earth, and gravitational forces pulled them back, generating friction within the Moon's interior and dissipating energy as heat. This process gradually slowed the Moon's rotation until its rotational period matched its orbital period, a state reached perhaps 3 billion years ago. Now the Moon rotates once every 27.3 days, exactly the time it takes to orbit Earth once, keeping the same hemisphere facing Earth permanently. This gravitational dance between Earth and Moon has shaped both worlds. The Moon stabilizes Earth's axial tilt, preventing wild swings in climate that would occur if Earth's axis wobbled chaotically. The tides mix ocean waters, distributing heat and nutrients, influencing ocean currents and marine ecosystems. Some biologists suggest that tidal pools may have played a role in the origin of life, providing environments where organic molecules could concentrate and react. From orbit, watching the Moon rise over Earth's limb, you witness the continuation of this ancient relationship. Two bodies locked in gravitational embrace, falling around each other, reshaping each other through forces that reach invisibly across the void. The Moon pulls Earth's oceans upward. Earth's rotation drags those bulges forward, pulling back on the Moon, propelling it slowly outward. It is a transfer of momentum that has continued for eons and will continue for billions of years more, until both worlds finally face each other eternally. Tidal forces at last reaching equilibrium. The timeline for Earth to become tidally locked to the Moon stretches far beyond any meaningful human timescale. Calculations suggest it would require approximately 50 billion years for Earth's rotation to slow enough that one hemisphere permanently faces the Moon. By that time, if such a future were even possible, Earth's day would equal the Moon's orbital period. Both would take roughly 47 current days to complete one cycle, with Earth rotating once while the Moon orbited once, and each world keeping the same face toward the other. But this future will never arrive. The Sun will not last that long. In roughly 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, swelling to perhaps 100 times its current diameter and engulfing Mercury, Venus, and possibly Earth itself. Long before tidal forces can lock Earth to the Moon, the solar system will undergo transformations so profound that predictions become meaningless. The gravitational dance between Earth and Moon will end, not in equilibrium, but in fire. Yet the process continues for now. Each day lasts a fraction longer than the day before, though the change is imperceptible. The Moon drifts outward, 3.8 centimeters farther each year, its gravitational influence diminishing incrementally as distance grows. Tides rise and fall, transferring momentum from Earth's spin to the Moon's orbit, continuing the ancient exchange that has shaped both worlds for more than 4 billion years. Other worlds in the solar system have reached equilibrium already. Pluto and its large moon Charon are mutually tidally locked. Each keeps the same hemisphere facing the other at all times. Standing on Pluto's surface, Charon would hang motionless in the sky, never rising or setting, forever occupying the same position. Standing on Charon, Pluto would similarly remain fixed. They orbit a common center of mass, bound together in a gravitational embrace so balanced that neither world ever sees the other's far side. All large moons in the solar system are tidally locked to their planets. Io, Europa, Ganymede, and Callisto show the same face to Jupiter always. Titan keeps one hemisphere towards Saturn. Triton orbits Neptune with its rotation synchronized to its orbital period. The process operates universally. Wherever a small body orbits close to a larger one, tidal forces eventually synchronize rotation and revolution. Beyond the solar system, many exoplanets discovered orbiting other stars are believed to be tidally locked, with one hemisphere permanently facing their host star and the other in eternal darkness. These worlds experience extremes, one side scorched by perpetual sunlight, the other frozen in endless night. Whether such planets could support life remains uncertain, though some models suggest that atmospheric circulation might moderate temperatures enough to create habitable zones along the terminator, the boundary between day and night. From the space station, you watch the moon rise over Earth's curved edge, two worlds, gravitationally bound, falling through space together. The tides below respond to the moon's pull, water rising and falling in an ancient rhythm. And far in the future, long after humans have gone, the same forces will continue, gradually slowing Earth's rotation, pushing the moon outward, until the sun's death ends the process forever. But there is another way to break free from gravitational bonds, not through waiting for tidal forces to weaken over eons, but through motion, through moving fast enough that gravity's curve becomes escapable. This is how spacecraft leave Earth, how probes journey to distant planets, how objects break the gravitational chains that would otherwise bind them forever to the worlds they orbit. You have been falling around Earth for weeks, locked in orbit at 7.7 kilometers per second. This velocity keeps you circling endlessly, tracing the same path again and again. But what if you wanted to leave? What if the station fired its engines and accelerated forward, increasing speed beyond the precise balance that maintains orbit? At what velocity would the curve of your trajectory straighten, transforming endless circling into a journey outward, away from Earth's gravitational grip? The answer is called escape velocity, the minimum speed required to break free from a gravitational field without further propulsion. For Earth, at the surface, this speed is 11.2 kilometers per second, or approximately 40,000 kilometers per hour. Reach this velocity and gravity can no longer pull you back. You will coast outward indefinitely, slowing gradually as Earth's gravity tugs against your motion, but never stopping completely, never falling back. Escape velocity is not about reaching a certain altitude where gravity disappears. Gravity extends infinitely outward from every mass, weakening with distance, but never truly vanishing. At the altitude where the International Space Station orbits, Earth's gravity is still 90% as strong as at the surface. Yet astronauts feel weightless because they fall continuously, matching the curve of space-time that Earth creates. Escape velocity is about motion, not position. It is about moving fast enough that your kinetic energy exceeds the gravitational potential energy binding you to Earth. The mathematics are straightforward. Gravitational potential energy depends on mass and distance. The farther from Earth's center, the less energy required to escape. Kinetic energy depends on velocity. When kinetic energy equals or exceeds gravitational potential energy, escape becomes possible. The formula emerges from conservation of energy. The escape velocity equals the square root of 2 times the gravitational constant times Earth's mass, divided by the distance from Earth's center. At Earth's surface, this calculation yields 11.2 kilometers per second. From orbit, the required velocity is lower. The space station already moves at 7.7 kilometers per second. To escape from this altitude, only an additional 3.2 kilometers per second is needed. The higher you climb before attempting escape, the less additional velocity is required, because gravitational potential energy decreases with distance. Geostationary satellites orbiting at 36,000 kilometers altitude need only 4.3 kilometers per second to escape, less than half the velocity required at Earth's surface. Escape velocity depends only on the mass of the body being escaped and the distance from its center. It does not depend on the mass of the escaping object. A grain of sand and a spacecraft require the same velocity to escape Earth, though the spacecraft requires far more energy because energy depends on both velocity and mass. A feather and a rocket, given identical speeds of 11.2 kilometers per second at Earth's surface, would both escape into space if no atmosphere resisted their motion. Earth's rotation provides a slight advantage for launches. At the equator, the surface moves eastward at 465 meters per second due to Earth's rotation. A rocket launched eastward inherits this velocity, reducing the additional speed needed to reach escape velocity to approximately 10.7 kilometers per second relative to the launch site. A rocket launched westward must overcome this rotation, requiring 11.7 kilometers per second relative to the surface. This is why launch facilities are built near the equator when possible. Cape Canaveral in Florida sits at 28 degrees north latitude, and the European Space Agency's primary spaceport in French Guiana lies just 5 degrees north of the equator. Different worlds require different escape velocities. The Moon, with only 1/80th of Earth's mass, requires just 2.4 kilometers per second to escape from its surface. Mars, roughly half Earth's diameter and 1/10 its mass, demands 5 kilometers per second. Jupiter, the most massive planet in the solar system, holds objects with tremendous force. Escape velocity from Jupiter's cloud tops reaches 59.5 kilometers per second, more than 5 times that of Earth. The Sun itself, from the distance of Earth's orbit, requires 42 kilometers per second to escape its gravitational influence entirely. These numbers reveal a pattern. The more massive the body and the closer you are to its center, the faster you must move to break free. Escape velocity from the surface of a neutron star, an object containing the mass of the Sun compressed into a sphere only 20 kilometers across, approaches half the speed of light. At the surface of a black hole, at the event horizon, escape velocity equals the speed of light itself, which is why nothing, not even light, can escape once it crosses that boundary. Rockets achieve escape velocity through staged propulsion. A typical launch vehicle consists of multiple stages, each containing fuel and engines. The first stage fires, accelerating the rocket upward through the densest part of the atmosphere. When its fuel is exhausted, the empty stage separates and falls away, reducing the mass that the remaining stages must accelerate. The second stage ignites, continuing the acceleration. For missions to the Moon or beyond, a third stage may fire after reaching orbit, providing the final push needed to achieve escape velocity. The energy required is enormous. Kinetic energy increases with the square of velocity. Doubling the speed requires 4 times the energy. For a 1,000 kilogram spacecraft to reach Earth's escape velocity of 11.2 kilometers per second, the kinetic energy required is approximately 62 million joules. This energy comes from burning fuel, typically liquid hydrogen and liquid oxygen, which combine to produce thrust. But fuel has mass, and that mass must also be accelerated, requiring more fuel, which requires still more fuel to accelerate it. A compounding problem that makes space travel enormously expensive. The tyranny of the rocket equation governs all launches. Konstantin Tsiolkovsky derived it in 1897, showing that the final velocity of a rocket depends on the exhaust velocity of its engines and the ratio of the rocket's initial mass to its final mass after fuel is burned. To achieve high velocities, most of the rocket's mass must be fuel. The space shuttle, at launch, weighed approximately 2,000 metric tons, but only 78 tons of that was the orbiter itself, the part that reached orbit and returned. The rest was fuel and disposable tanks. Spacecraft returning to Earth do not need to fight against escape velocity. They already orbit at high speed. By firing engines in the opposite direction of travel, they slow down just enough to let gravity pull them back into the atmosphere. The atmosphere does the rest. Friction converting orbital velocity into heat until the spacecraft slows to subsonic speeds and can deploy parachutes. Gravity, having pulled the spacecraft back, delivers it safely to the surface, completing the cycle. Spacecraft propulsion systems divide into three main categories: chemical, electric, and propellantless. Chemical propulsion has dominated spaceflight since its beginning, burning fuel to produce thrust through controlled explosions. These systems generate enormous force, enough to lift thousands of tons off the launch pad and accelerate them to orbital velocity within minutes. Chemical rockets produce thrust by expelling hot gases through a nozzle at high speed. The principle is Newton's third law. For every action, there is an equal and opposite reaction. The rocket pushes gas backward, and the gas pushes the rocket forward. The most common chemical propulsion systems use either solid or liquid propellants. Solid rocket motors contain fuel and oxidizer mixed together in a solid form, typically rubber-like compounds combined with ammonium perchlorate and powdered aluminum. Once ignited, they burn until depleted. They cannot be throttled or shut off. The Space Shuttle's two white solid rocket boosters produced most of the thrust during the first 2 minutes of flight, each burning through 500 metric tons of propellant before separating and falling back to Earth. Solid motors are simple, reliable, and can be stored for years without degradation, but their inability to be controlled once ignited limits their applications. Liquid propellant systems offer more flexibility. They store fuel and oxidizer separately, typically liquid hydrogen and liquid oxygen for high-performance engines, or kerosene and liquid oxygen for first stages where density matters more than specific impulse. Pumps feed these propellants into a combustion chamber where they mix and ignite, producing temperatures exceeding 3,000 degrees Celsius. The resulting gases expand through a nozzle, accelerating to several kilometers per second as they exit. These engines can be throttled, shut down, and restarted, providing precise control over thrust and trajectory. The Saturn V moon rocket used liquid oxygen and refined kerosene in its first stage, liquid oxygen and liquid hydrogen in its upper stages, achieving the velocity needed to send astronauts beyond Earth's gravitational influence. Monopropellant systems use a single chemical that decomposes when exposed to a catalyst. Hydrazine is the standard, a toxic, corrosive liquid that breaks down into hot gases when it contacts iridium catalyst. These systems are simpler than bipropellant engines because they require only one propellant tank and no combustion chamber, but they produce lower thrust and specific impulse. Spacecraft use them for attitude control and small orbital adjustments, where simplicity and reliability outweigh performance. The space station uses hydrazine thrusters for minor corrections to its orbit and orientation. Electric propulsion trades thrust for efficiency. Ion engines accelerate charged particles using electric fields, ejecting them at velocities far exceeding those possible with chemical rockets, up to 90 kilometers per second compared to 4 or 5 for chemical engines. This high exhaust velocity means far less propellant is needed to achieve the same change in velocity. But electric engines produce minuscule thrust, typically measured in millinewtons, roughly the weight of a sheet of paper pressing against your hand. They cannot lift anything off Earth's surface. They work only in space, where even tiny thrust applied continuously over months or years can accelerate a spacecraft to enormous velocities. NASA's Dawn spacecraft used ion propulsion to visit the asteroids. Vesta and Ceres between 2007 and 2018, becoming the first mission to orbit 2 different extraterrestrial bodies. Its engines consumed only 425 kilograms of xenon, propellant over the entire 11-year mission. Less fuel than a car uses in a year, yet provided enough thrust to change velocity by more than 11 kilometers per second. Chemical rockets would have required tons of propellant to achieve the same result, making the mission prohibitively expensive or impossible. Hall effect thrusters, another electric propulsion technology, use magnetic fields to trap electrons and create a region of ionized gas. The ions accelerate through an electric field and exit at high velocity. These engines provide slightly more thrust than ion engines while maintaining high efficiency. The space station periodically uses visiting spacecraft equipped with electric thrusters to perform gentle reboosts, maintaining altitude without the violent jolts of chemical propulsion. Cold gas thrusters represent the simplest propulsion technology. Pressurized gas expelled through a nozzle, nothing more. No combustion, no catalysts, no ionization. Just gas expanding into vacuum. Performance is poor. Specific impulse around 50 seconds, far below chemical or electric systems. But the simplicity makes them attractive for small satellites where mass and complexity must be minimized. CubeSats often carry small tanks of nitrogen or other gases, using them for basic attitude control and momentum dumping. The time has come to leave orbit. After weeks or months circling Earth, the command comes from Mission Control. Prepare for deorbit burn. The spacecraft rotates, orienting its engines opposite to the direction of travel. The thrusters fire. Not for long, perhaps 2 or 3 minutes. But that is enough. The velocity decreases by only 128 meters per second, less than 2% of orbital speed. But this small change breaks the delicate balance between falling and circling. The spacecraft begins to descend. The descent is gradual at first. The trajectory curves downward, dipping into the uppermost reaches of Earth's atmosphere at an altitude of approximately 120 kilometers. Here, air molecules are so sparse that 1 cubic meter contains fewer particles than a good vacuum chamber on Earth's surface. But the spacecraft is moving at nearly 8 kilometers per second, more than 23 times the speed of sound. At this velocity, even the tenuous wisps of atmosphere create resistance. Atmospheric drag begins. The spacecraft pushes through air molecules, compressing them against its leading surface. This compression generates heat, enormous destructive heat. Contrary to common belief, most of the heat during re-entry does not come from friction between the spacecraft and air. It comes from compression. As the spacecraft rams through the atmosphere at hypersonic speeds, air molecules cannot move out of the way fast enough. They pile up, compress, and their temperature skyrockets according to the laws of thermodynamics. The bow shock wave forms, a boundary where compressed air reaches temperatures exceeding 10,000 degrees Celsius, hot enough to break molecular bonds and ionize the gas into plasma. This plasma envelops the spacecraft in a glowing sheath that blocks radio communications for several minutes, creating the infamous re-entry blackout. The plasma radiates energy across the electromagnetic spectrum: visible light, ultraviolet, infrared. An observer on the ground might see a meteor-like streak across the sky, brilliant orange or white, trailing behind the descending spacecraft. The heat is relentless. Peak heating occurs when the spacecraft reaches an altitude of about 60 to 70 kilometers, still traveling at several kilometers per second. At this point, the spacecraft's leading surfaces experience temperatures that would vaporize most materials instantly. Steel melts at 1500 degrees Celsius, aluminum at 660 degrees, even titanium liquefies at 1660 degrees. Without protection, the spacecraft would disintegrate. Protection comes from thermal shields, specialized materials designed to absorb, block, or dissipate the tremendous heat flux. The space shuttle used thousands of silica tiles on its underside and wings, each one custom-shaped to fit specific locations on the airframe. These tiles are remarkable materials, ceramic foam so porous that 90% of their volume is empty space, making them excellent insulators. Even when heated to glowing red on one side, the opposite side remains cool enough to touch. The leading edges of the shuttle's wings, where temperatures reached the highest, used reinforced carbon-carbon composite, a material that maintains structural strength above 2000 degrees Celsius. Other spacecraft use ablative heat shields, materials designed to char and vaporize during re-entry, carrying heat away as they do so. The Apollo command modules used phenolic resin impregnated into a fiberglass honeycomb structure. As the shield heated, the resin decomposed into gases that expanded outward, forming a protective boundary layer between the plasma and the spacecraft's structure. The process was violent but effective. By the time Apollo capsules splashed down in the Pacific Ocean, their heat shields were charred and pitted, several centimeters of material ablated away, but the crew inside remained safe. Modern spacecraft like SpaceX's Crew Dragon use an updated version of ablative protection called Pika-X. Phenolic impregnated carbon ablator, version X. This material can withstand multiple re-entries, allowing the capsules to be refurbished and reused on future missions. The heat shield chars during descent, but enough material remains intact that after inspection and minor repairs, the same shield can protect the capsule through additional re-entry events. The re-entry trajectory must be precise, too steep, and the spacecraft plunges into dense atmosphere while still traveling at orbital velocity, generating heat faster than any shield can dissipate it. The vehicle burns up, disintegrating in seconds, too shallow, and the spacecraft skips off the atmosphere like a stone skipping across water, bouncing back into space with insufficient velocity to return. The Apollo command modules approached at an angle between 5.3 and 7.7 degrees, a narrow corridor that required careful control during the deorbit burn. As the spacecraft descends below 70 kilometers, atmospheric density increases rapidly. Drag becomes the dominant force, slowing the vehicle more efficiently than any rocket engine could. The deceleration is intense, up to 6 or 7 times Earth's gravity for crew capsules, though the space shuttle experienced gentler deceleration, rarely exceeding 2 Gs because of its aerodynamic shape and shallow glide path. Astronauts lie on their backs during re-entry, pressed into their seats by the force, breathing with effort as their chest feels compressed by an invisible weight. By 50 kilometers altitude, velocity has dropped below supersonic speeds. The plasma sheath dissipates and radio communications resume. The spacecraft is no longer falling freely through vacuum or near vacuum. It is descending through air thick enough to provide aerodynamic control, though still too thin to breathe. Parachutes deploy in stages. First come small drogue chutes, stabilizers that prevent tumbling, and begin slowing the descent. The Apollo command modules deployed 2 drogue parachutes at about 7 kilometers altitude when the capsule was still falling at 100 meters per second. The drogues reduce speed and stabilize the capsule's orientation. Next, pilot chutes deploy. Small parachutes whose sole purpose is to pull out the main parachutes. Finally, the main chutes unfurl. 3 massive canopies, each one 35 meters in diameter for Apollo missions, slowing the capsule to a gentle descent rate of about 8 meters per second. Modern Crew Dragon capsules use 4 main parachutes, providing redundancy in case one fails. The descent becomes peaceful. After the violence of re-entry, the chaos of heat and plasma and roaring air, the spacecraft now drifts downward beneath billowing fabric, swaying gently in the wind. The crew can see the ocean or land approaching, can feel gravity's full weight returned after weeks or months of weightlessness. Splashdown occurs when the capsule hits water, sinking partially before flotation devices inflate and stabilize it on the surface. Water is preferable to land for crew capsules because it decelerates more gently, absorbing impact energy through displacement rather than compression. The Soviet Soyuz capsules land on solid ground in Kazakhstan, using small retro-rockets that fire just before touchdown to cushion the impact, combined with shock absorbers in the seats. The landing is rough. Cosmonauts describe it as similar to a car crash, jarring but survivable. Recovery teams arrive within minutes. Helicopters for ocean landings, ground vehicles for land touchdowns. Divers secure the floating capsule, attach flotation collars, and assist the crew in exiting. The astronauts emerge weak, unsteady, relearning how to stand under gravity's insistent pull. They have returned. The endless fall has ended. Gravity, having released them briefly into orbit, reclaims them, pulling them back to the surface where humans evolved, where weight and falling and standing all carry their original meanings. The recovery vessel positions itself within a few hundred meters of the floating capsule, its crew already deployed on fast boats that race across the water toward the spacecraft. The first boat arrives within minutes, its operators wearing protective gear as they approach cautiously. Their initial task is critical, testing the air around the capsule for traces of hypergolic propellants, toxic chemicals that power the spacecraft's maneuvering thrusters. Nitrogen tetroxide and hydrazine are corrosive and deadly if inhaled. The crew checks with handheld sensors, moving around the capsule's perimeter, ensuring no leaks have contaminated the immediate area. Once the all clear is given, the second fast boat moves in to recover the parachutes, which have detached from the capsule and now float on the surface like enormous jellyfish, their fabrics spread across the water. These parachutes are valuable. Each one costs hundreds of thousands of dollars and can be refurbished for future missions. Crews attach lines and drag them toward the recovery ship where they will be hauled aboard, rinsed with fresh water to remove salt, and inspected for damage. Meanwhile, the main recovery vessel maneuvers closer. Swimmers in the water attach cables and stabilization devices to the capsule, guiding it into position beneath the ship's crane. Hydraulic arms extend, clamps engage, and slowly, with water streaming from its heat shield, the spacecraft rises from the ocean and swings onto the deck. The entire process from splashdown to capsule on deck takes approximately 45 to 60 minutes, though this varies depending on sea conditions and spacecraft status. Crew egress must happen quickly. NASA requires astronauts to be removed from the Dragon capsule within 60 minutes of splashdown. Medical teams stand ready as technicians approach the capsule, now secured in its cradle on deck. Seawater is hosed off the metallic surfaces. Salt water corrodes metal, and preservation of the spacecraft for potential reuse demands immediate rinsing. The hatch is opened from outside. Fresh air rushes into the capsule, replacing the stale atmosphere that has sustained the crew during their descent. The astronauts emerge slowly, assisted by medical personnel who help them from their seats and guide them through the hatch. They are weak, legs tremble, balance fails. After weeks or months in weightlessness, their bodies have forgotten how to stand. The cardiovascular system, adapted to pumping blood without fighting gravity, now struggles to maintain adequate pressure to the brain. Some astronauts cannot stand at all immediately after landing. They sit, supported, waiting for their hearts to remember their earthbound rhythm. Medical evaluations begin immediately. Blood pressure, heart rate, basic neurological assessments. The astronauts are moved to a medical facility on the ship where they can lie down, receive intravenous fluids if needed, and begin the process of readapting to gravity. Within hours, a helicopter arrives to transport them back to land, to Kennedy Space Center or another facility, where they will undergo more extensive medical monitoring over the following days and weeks. The capsule remains on the recovery ship, secured and guarded. It will be transported back to port, where engineers will inspect every system, download flight data, analyze the condition of the heat shield, and determine whether the spacecraft can be refurbished for another mission. Some capsules fly multiple times, others retire after a single flight. Their heat shields too degraded, their systems too worn to trust with human lives again. For the astronauts, recovery from spaceflight takes time. The puffy face deflates within days as fluids redistribute normally. Balance returns within a week or two as the vestibular system recalibrates. But bone density and muscle mass require months to rebuild, even with aggressive physical therapy and exercise. Some effects persist longer. Vision problems can remain for years. Arterial stiffness may never fully reverse. The body bears permanent marks from its time in orbit, subtle reminders that humans evolved under gravity's constant pressure and suffer consequences when that pressure disappears. Yet they adapt. The body, remarkably resilient, gradually returns to its terrestrial configuration, and the astronauts carry something else back with them. Memories of falling endlessly around Earth, of seeing 16 sunrises each day, of floating weightless through curved modules while the planet turned below. They have experienced what few humans ever will: liberation from gravity's insistent pull, and the strange, peaceful sensation of perpetual freefall. Gravity, as experienced on Earth or in orbit around it, is a gentle force. It pulls objects downward at 9.8 meters per second squared. It keeps planets circling the sun at measured, predictable velocities. It creates tides that rise and fall in predictable rhythms. But elsewhere in the universe, gravity exists in forms so extreme that they defy common intuition, warping spacetime so severely that even light cannot escape. These regions are called black holes, concentrations of matter so dense that they create gravitational wells from which nothing can return. At their boundaries lies the event horizon, a surface marking the point of no return. Cross this threshold moving inward, and no amount of thrust, no velocity less than the speed of light, can carry you back out. The escape velocity at the event horizon equals exactly the speed of light, and nothing in the universe can move faster. Black holes form when massive stars exhaust their nuclear fuel and collapse. During a star's life, fusion reactions in its core generate outward pressure that balances the inward pull of gravity. The star exists in equilibrium, neither collapsing nor expanding. But when fusion ceases, pressure disappears. Gravity takes over completely, compressing the star's core with unstoppable force. For stars between 8 and 20 times the Sun's mass, this collapse produces a supernova, an explosion that ejects the star's outer layers into space, while the core implodes to form either a neutron star or a black hole. If the core's mass exceeds approximately 3 times the Sun's mass, even neutron degeneracy pressure cannot prevent further collapse. The core continues to compress, passing through every state of matter, solid, liquid, plasma, until it reaches a point where normal physics breaks down entirely. At the center lies the singularity, a point of infinite density where all the mass of the collapsed star is compressed into zero volume. The mathematics describing this state produce infinities, suggesting that general relativity, which successfully predicts nearly everything else about gravity, reaches its limits here. Physicists suspect that a complete theory of quantum gravity will be needed to understand what truly occurs at a singularity, but such a theory does not yet exist. The event horizon forms at a specific distance from the singularity, determined solely by the mass of the black hole. For a non-rotating black hole, this radius is called the Schwarzschild radius, calculated as twice the gravitational constant times the mass divided by the speed of light squared. For a black hole with the Sun's mass, the Schwarzschild radius would be approximately 3 kilometers. Compress the Sun into a sphere 6 kilometers across, and it becomes a black hole. For Earth, the Schwarzschild radius is less than 1 centimeter. Compress the entire planet into a sphere smaller than a marble, and gravity would become strong enough to trap light. The simplest black holes possess only mass, no electric charge, no rotation. These Schwarzschild black holes are spherically symmetric, and their gravitational field at any distance is identical to that of any other object with the same mass. This means that if the Sun suddenly collapsed into a black hole, which it cannot because it lacks sufficient mass, Earth's orbit would remain unchanged. The gravitational pull at Earth's current distance would be identical to what it experiences now. Black holes do not suck in matter from afar any more than normal stars do. Only near the event horizon does their gravity become inescapable. Most black holes, however, rotate. Stars spin, and when they collapse, conservation of angular momentum causes the resulting black hole to spin even faster, much like a figure skater pulls in their arms to accelerate a pirouette. These rotating black holes, called Kerr black holes, are more complex than their non-rotating counterparts. They possess not just a singularity and event horizon, but also an ergosphere, a region outside the event horizon where space-time itself is dragged around the black hole. Within the ergosphere, nothing can remain stationary. Space-time rotates with the black hole, and any object must move along with it, regardless of how its engines fire or how it attempts to resist. This frame-dragging effect becomes so intense near the event horizon that an object would need to travel faster than light in the opposite direction just to stand still. Yet escape from the ergosphere remains possible. Objects can enter, extract energy from the black hole's rotation through a process called the Penrose process, and leave with more energy than they brought in. This extraction of rotational energy gradually slows the black hole's spin. Black holes are classified by mass into distinct categories. Stellar mass black holes form from collapsing stars and typically range from 3 to several dozen times the Sun's mass, with event horizons measuring tens of kilometers across. These represent the smallest black holes that can form through stellar collapse, as less massive stellar cores become neutron stars instead. Supermassive black holes occupy the centers of most large galaxies, including the Milky Way. These monsters contain millions to billions of solar masses, compressed into regions comparable to the solar system. Sagittarius A star, the supermassive black hole at the Milky Way's center, weighs approximately 4 million times the Sun's mass, yet would fit within a volume that could hold only a few million Earths, a density almost incomprehensible. Despite their name, supermassive black holes are not denser than stellar black holes. Their event horizons are simply larger, proportional to their mass. Between these extremes lie intermediate mass black holes, containing hundreds to hundreds of thousands of solar masses. These remain somewhat mysterious. Their formation mechanisms are less understood, and detecting them proves difficult because they produce weaker gravitational effects than supermassive black holes, while being rarer than stellar mass ones. Theoretical micro-black holes, if they exist, would contain masses smaller than Earth's and have event horizons measured in fractions of a millimeter. Some physicists speculate these might have formed in the early universe's extreme conditions, though none have been observed. A micro-black hole with a mountain's mass would be no larger than an atom. Approaching a black hole reveals gravity's most extreme effects. Far away, the gravitational field feels no different from any star of equivalent mass, but closer in, tidal forces, the difference in gravitational pull across distance, become dramatic. For a stellar mass black hole, these forces would become lethal while still far outside the event horizon. The difference in gravitational acceleration between an astronaut's feet and head would stretch the body like taffy, a process physicists grimly call spaghettification. Long before reaching the event horizon, any structure, spacecraft, human body, even atoms, would be torn apart by the gradient in gravitational force. Supermassive black holes, paradoxically, offer gentler conditions near their event horizons. The tidal forces depend not just on mass but on the density gradient, how rapidly gravity changes across distance. A supermassive black hole has an event horizon so large that the gravitational gradient across a human body would be negligible even at the boundary. An astronaut could theoretically cross the event horizon of a billion solar mass black hole without experiencing fatal tidal forces, at least not immediately. They would pass through unharmed, unaware that they had just crossed the point of no return. Only later, as they fell deeper and approached the singularity, would tidal forces grow strong enough to destroy them. Black holes cannot be seen directly. They emit no light, but astronomers detect them through their effects on surrounding matter. When a black hole exists in a binary system with a normal star, material from the companion star can be pulled toward the black hole, forming an accretion disk of gas spiraling inward. Friction within this disk heats the gas to millions of degrees, causing it to emit intense X-rays detectable by space-based observatories like Chandra and XMM Newton. Cygnus X1, one of the first black hole candidates identified, was discovered through its X-ray emissions in 1964. Observations of its companion star's orbital motion revealed it was orbiting an invisible object approximately 15 times the Sun's mass, far too massive to be a neutron star. Gravitational waves provide another detection method. When two black holes spiral toward each other and merge, they create ripples in spacetime that propagate outward at the speed of light. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected its first black hole merger in September 2015. Two black holes with masses of 36 and 29 solar masses colliding and forming a single black hole of 62 solar masses. The remaining 3 solar masses converted entirely into gravitational wave energy, radiated into space in a fraction of a second. This detection confirmed a prediction Einstein made a century earlier and opened a new era of astronomy. Supermassive black holes reveal themselves through their effects on stars orbiting near galactic centers. At the Milky Way's core, astronomers have tracked individual stars for decades, watching them orbit an invisible point at tremendous velocities. The star S2 completes one orbit every 16 years, reaching speeds up to 5,000 kilometers per second at its closest approach. The only explanation for such extreme velocities is a supermassive black hole, Sagittarius, a star containing 4 million solar masses compressed into a region smaller than Mercury's orbit. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. Not the black hole itself, but the dark silhouette it creates against the glowing accretion disk surrounding it. The target was M87 star, the supermassive black hole at the center of galaxy Messier 87, located 55 million light-years away. The black hole weighs 6.5 billion solar masses, and its shadow spans a diameter of about 40 billion kilometers, nearly 3 times the size of Pluto's orbit. The image showed exactly what general relativity predicted: a dark circle surrounded by a bright ring of photons bent by the black hole's gravity. Black holes do not last forever. Stephen Hawking demonstrated in 1974 that quantum effects near the event horizon cause black holes to emit radiation and gradually evaporate. This Hawking radiation is extraordinarily weak for stellar mass and supermassive black holes. A solar mass black hole would take 10 or 67 years to evaporate, far longer than the current age of the universe. But smaller black holes radiate more intensely, their temperature inversely proportional to their mass. A black hole the mass of a mountain would glow white hot and evaporate in seconds. Yet even as black holes evaporate, they reveal something fundamental about the universe. They demonstrate gravity at its most extreme, where space-time curves so severely that it closes off regions from the rest of existence. They test the limits of general relativity and hint at deeper physics yet to be understood. And they remind us that gravity, the force that keeps your feet on the ground and holds the moon in orbit around Earth, is the same force that can trap light itself, bending space-time into structures so extreme that escape becomes impossible.